So good evening to Ananda. Good evening. Yeah. Good evening. Good evening to Ananda. So till now we have started this equal area criteria. Till now we have started that equal area criteria, and we have seen. We have seen till now. I think 5 case studies. 5 case studies. First case study we said a sudden and large increment in the mechanical input to the alternator. Next, we studied transient stability analysis with respect to fault. Then recently we studied that transient stability analysis with respect to removal of a transmission line. Removal of a transmission line wire. Okay. See, the next case study, what we are going to take up is a sudden and large increment in the mechanical load, on the shaft of the synchronous motor. Okay. Before moving to that study of the synchronous motor disturbance, transient stability, let us take up the swing equation and all with respect to synchronous motor first. Okay. Already we discussed, already we have taken the derivation of this one, but now I want to recall them. Yeah. So just let's take a small heading here. Synchronous motor swing equation. Just as a recap, I am saying this one. Synchronous motor swing equation. Yeah, look here. So this is a synchronous motor connected to infinite bus bar. Yeah, Devika, MV, Devika, please call to my number or just put a text message to me. I will help you. 96184-61918. This is my mobile number. Just put a text message to me in the WhatsApp or Telegram. I will help you. Okay. Yeah. Listen here. Listen. So it was a synchronous motor, and infinite bus voltage mod V at an angle 0 degree, and this is mod E at an angle minus delta internal voltage. Okay. And angular momentum of this machine is m. Yeah. Now, first, if you write up the d omega by dt, rate of change in the speed of the motor, it is PA by m. Accelerating power PA by m. Series. This is electrical power input PE. Mechanical load we have as PS. Then what is the accelerating power PA? We said input minus output. Electrical power input minus mechanical power output. Electrical power input minus mechanical power output. Yeah. And you see, the swing equation, the other way of writing the swing equation, m d square theta by dt square is equals to accelerating power by m. And we have one more expression to say d delta by dt. Which is nothing but synchronous speed omega s minus omega. But earlier in case of generator, we said it is omega minus omega s. But in this case of motor, it will be omega s minus omega. I said many times that always our transient stability analysis will be running along with these two statements only. One, is a calculation of d omega by dt. Next one, calculation of d delta by dt. Means checking how is d omega by dt. Is it positive or negative? Based on that, we decide whether the speed is increasing or decreasing with respect to synchronous speed. And based on that, omega more than omega s or less than omega s, we are capable to decide that d delta by dt value. Based on that, we decide whether the delta is increasing or decreasing. Okay, d square theta by dt square. Yeah, I think all of you getting this one. Now, as a recall of whole equal area criteria, we'll discuss about this synchronous motor, so-called the last case study number 6. Yeah. So, case study number 6, we have a sudden and large increment in mechanical load on synchronous motor shaft. Connected to infinite bus bar. Synchronous motor is connected to infinite bus bar. That's the meaning. Yeah. So let's continue. Let's continue with this. So this is a synchronous motor we have. Sorry, infinite bus bar, and that's connected to the synchronous motor as we said just now. And this is a mechanical load on the motor shaft, indicating the letter PS. Electrical power input I am showing as PE. Electrical power input is PE. First of all, that electrical power equation, let me say first it is mod V at an angle 0 degree, and the internal voltage of motor is mod E at an angle delta, and this motor is having some reactance. Motor might be having some reactance, or between infinite bus bar and synchronous motor, we might be having some reactance network. So first electrical power equation, if you write electrical power equation, if you write PE is equals to mod V into mod E by that whole reactance, I will say simply X into sine delta. Sine of 0 minus of minus delta. 0 minus of minus delta, it will be sine delta. You write this simply like P maximum into sine delta. P maximum into sine delta. That's the electrical power equation. Yeah. See, do you have any disturbance on the network in this case? Do you have any disturbance on the network in this case? No, we don't have any disturbance on the network. See, even you increase the load on the shaft of the motor or decrease the load on the shaft of the motor, this P maximum value is not going to be changed. Means our power angle curve will be remains same. But because of this load change what you are making, definitely there will be a variation in the accelerating power. Because of that, speed of the motor will vary, and d delta by dt will not become 0. D delta by dt may be positive or may be negative, because of the delta angle is going to be changed. According to the delta change, electrical power value is also expected to be changed. Okay, yeah. So let us write up the initial conditions what we have before creating the disturbance. I am going to take up the initial conditions. Similar to the previous studies and all which we have done. Initial conditions. Yeah, see this first one. Rotor angle is delta naught. Same things which we have discussed earlier. Rotor speed omega equals to omega s, we said. Okay, next, mechanical load on the motor shaft. Is PS1. It's the initial mechanical load on the motor shaft. Next one, electrical power input in the initial stage. Is PE at an angle of delta naught, you should say, which is nothing but P maximum sine delta naught. But as far as this initial stage of operation is concerned, this mechanical load value as well as electrical power output, these two are exactly equal. Right? So according to this present initial condition, we can write mechanical load value and electrical power output. These two are exactly equal. Thereby, you can write delta naught value as sine inverse of PS1 by P maximum. Sine inverse of PS1 by P maximum. Okay. Done. Next. Disturbance. I am writing now. Disturbance. See, mechanical load on the motor shaft was suddenly increased from a value PS1 to a new number PS2. Okay. Mechanical load on shaft of the motor was increased from PS1 to a number PS2. Okay, rather than changing that notation and all, I am taking the same notation as PS as mechanical load. Okay, right. So PS2 greater than PS1. Tell me now, tell me. But as you know, just after making that increment, do we expect any change in the rotor speed instantaneously? No, because of the inertia of the rotor speed will not change instantaneously. If it is the case, rotor angle also remains same at an angle of delta naught at that instant. Okay, yeah. So I can say, so there is no instantaneous change. There is no instantaneous change in rotor speed and rotor angle. There is no instantaneous change in the rotor speed and rotor angle. In bracket you write due to inertia. Okay, due to inertia. Next thing. But you know, in a simple way, mechanical load on the shaft was more, right? PS1 to a value, PS2 it was increased. Because of that, your electrical power will be remains at a value of P maximum sine delta naught. But mechanical load was increased. So mechanical output is more compared to electrical power input. So what will happen? That input minus output negative. So accelerating power will become negative. If accelerating power is negative, d omega by dt value will be negative. Omega starts decreasing from where? Omega s. So omega starts decreasing from omega s, then obviously d delta by dt will turn to positive because it is omega s minus omega. That will become positive. Don't bother, I will write all the things. Just listen. So if d delta by dt is positive, delta will increase from where? Delta naught. As in when delta is increasing from delta naught, obviously electrical power will change according to this curve equation P maximum sine delta. Okay, to show these variations, first I will show the power angle curve, electrical power input curve, and I will show the mechanical output lines, and we will see how the angle and speeds are going to be changed. Okay, yeah. So let's take here. So that power angle curve I am taking up, right? So it's a delta axis I have, and we have power axis here. Power axis, and it is delta axis. First, I am saying power angle curve, P maximum sine delta curve I am showing here. Kindly observe this one. It's a electrical power input curve. Input curve, P. Okay, next, it's a P maximum value, of course, maximum power transfer. Capacity of the network, you can say P maximum. Then next, mechanical load on the motor shaft, PS1. Initial mechanical load is PS1. Just observe. It is our initial mechanical load, PS1. And this is our initial operating point. I can call it is A. Initial operating point as A. And associating angle will be delta naught. And speed at that particular location point A will be omega is equals to omega s. Next thing. All of a sudden, mechanical load was increased from PS1 to PS2. All of a sudden, mechanical load value was increased from PS1 to PS2, something like this. Right? So this is the mechanical load, new mechanical load on the motor shaft. We are saying it is a PS2. Saying that as PS2. Okay, next thing. Listen. I'll write at point A, just after making that load increment. Yeah, kindly draw this one quickly. Please make it quick. Draw this one quickly. Yeah, once if you have completed, please raise your hands. I will move to next slide. Okay, good. So at point A, just after load increment, load increment. Okay. Next, look here. So accelerating power, if you talk, or first you write rotor angle, it will be delta naught only. And rotor speed, it will be synchronous speed. Rotor speed, it will be equals to synchronous speed only. But accelerating power of the rotor body, on the rotor body also you can say PA equals to electrical power input, that is P maximum sine delta naught right now, minus mechanical load is PS2. Electrical power input is P maximum sine delta naught, mechanical load is PS2. How is this number coming? It will be definitely negative. Negative means we have a deceleration for the rotor body. Deceleration for the rotor body. And if you have deceleration, obviously at this point, d omega by dt number, which is PA by M, negative. D omega by dt number, PA by M, that is negative. What is d delta by dt? Omega s minus omega, present speed also synchronous speed only. So it will be remain 0. D delta by dt is 0 at that point A. At that point A we are talking. But d omega by dt value was negative. Now what you should say is from point A, omega starts decrease from omega s. Because of that, d delta by dt is positive. Delta will start increase, we should say. Okay? Yeah, let me write. From point A onwards, omega decreases from omega s. That implies omega less than omega s occurs. Okay, so that implies d delta by dt number will turn into positive because it is omega s minus omega. You write better, omega s minus omega, that is positive. Omega s minus omega, that is positive, means you can say delta value will increase from delta naught. Increases from delta naught. Delta value will increase from delta naught. Fine, good. Yeah, please make it quick. Delta will increase from delta naught. So I'm showing in the previous slide now. Delta starts increase from delta naught like this. Because of that increment in the angle, electrical power PE will vary along this power angle curve. Electrical power will vary along this power angle curve. But you observe now, because of the mechanical load increment what you have made, corresponding electrical power input is increasing. But still, electrical power input minus mechanical load, that is negative value. This is your electrical input, but this is your mechanical load. So input minus output, that is negative. So omega continue to decrease. Actually, omega value will continue to decrease. Even though you are saying electrical power is increasing, but still we have PA value negative means omega decreasing. Omega decreasing in the sense, omega value will be less than omega s. If omega is less than omega s, d delta by dt is positive, delta will continue to increase. Okay? Yeah. All of you just answer to my question. What I am asking you here. Just I am stopping at some point like this. Stopping at this point. Okay. Could you please tell me what is speed at this point? What is the value of speed at this point? Less than omega s or more than omega s? How is the speed at this point? Is it less than omega s or more than omega s? Less than omega s. Good. How is the accelerating power? Positive or negative? Accelerating power. Positive or negative? Negative. Accelerating power is negative. Good. Okay. Listen. From that point onwards, how is the movement? How is the omega variation? How is the delta variation? That we should ask ourselves. If you ask like that, then this analysis will be a bit easy for us all the time. Okay, by standing here, PA is negative. So omega will decrease further. From the point onwards, omega will decrease further. Already omega less than omega s, omega will decrease further and omega will be less than omega s only. If omega is less than omega s, delta by dt is positive. Delta will continue to increase. Because of that, operating point will move on the power angle curve, something like this, right? And we are touching to one point here. What is the speciality of this point? What's the speciality of this point we have? Electrical power input value, mechanical load value, both are exactly equal. Both are exactly equal. Accelerating power is equals to 0. Accelerating power equals 0. But what is the value of speed at that point? What's the value of speed at that point? It will be less than synchronous speed only, right? Omega will be less than synchronous speed. So as omega is less than omega s, the operating point will not stop there. Means rotor will not stop at the point itself. And as omega less than omega s, d delta by dt is still positive. Delta will increase beyond that point. Means first I'll show this point corresponding angle is delta 1. So delta will increase beyond delta 1, you can say. So if delta is increasing beyond delta 1, operating point will move something like this. See, if the operating point is moving ahead of B because of delta increment, you observe that electrical input is becoming more compared to mechanical. Electrical input is becoming more compared to mechanical load, means accelerating power will be positive. Accelerating power is positive. So omega starts increasing from the point B onwards. Okay, omega starts increasing in this particular zone. So omega starts increasing, but it won't catch up synchronous speed very quickly. It will take some time. To catch up the synchronous speed. In the time duration, obviously omega less than omega s only. D delta by dt is positive. Delta will continue to increase up to the point wherever you touch omega equals to omega s. Following all of you. And who will decide whether we are going to touch that omega equals to omega s or not? Means it will be obviously areas. Areas is the thing which is going to decide whether we are going to touch omega equals to omega s or not. Okay, one more thing. As you know, A to B, omega is decreasing. From B onwards, omega is increasing. Means at point B, we might be expecting that we are touching minimum speed. We might be touching the minimum speed at this point B. Minimum speed we are touching at the point B. Okay, let me continue. The next slide. A to B I will write now. A to B, I'm writing here. A to B. If you take up the accelerating power PA, which is electrical power input minus mechanical load is PS2. That value was negative here. If accelerating power is negative, d omega by dt, which is PA by M, negative number, right? So omega value was decreasing in that zone. Omega less than omega s, okay? And d delta by dt, which is omega s minus omega, that number was positive. Delta value was increasing in that zone. From A to B, we can say. Now, at that point B, where you are standing, at that point B, rotor angle is delta 1. Rotor angle was delta 1. Okay, it is a constant angle at that point B. Okay, and the rotor speed, it is less than omega s, but we have written that as minimum speed because already we explained the thing how it is going to come as minimum, because from that point onwards it is increasing. Okay, next, if you calculate accelerating power, electrical power input P maximum sine delta 1, mechanical power demand PS2, and these two are exactly equal. So accelerating power is 0. In the sense you write neither acceleration nor deceleration. And if you calculate d omega by dt number, that is PA by M, which is 0. D omega by dt number is 0. And if you calculate d delta by dt, which is omega s minus omega, d delta by dt number, omega s minus omega, that number is still positive at this location B, d delta by dt number is positive. D delta by dt number is positive. So from the point B onwards, just observe. From the point B onwards, delta starts increase from delta 1. Delta starts increase from delta 1. So definitely delta will become greater than delta 1, and we will write the statements whatever it is necessary. Please complete it. Please complete it quickly. Yeah, once after completion, please raise your hands. We'll be moving to next slide. Good. Yeah, so I'm writing now. So as you know, d delta by dt is positive. From point B onwards, delta increases beyond delta 1. Delta increases beyond delta 1 because of the delta increment. If I calculate accelerating power, right, that is becoming positive. Pa equals to positive will occurs. If Pa is positive, d omega by dt number is positive, and omega value was increasing. Omega value was increasing, but still omega is less than omega s. I'll write that in this manner. But still omega is less than omega s. But still omega less than omega s. Initial mechanical power is PS1. Initial mechanical power is PS1. Okay, I'm showing previous slide. I think still somebody is writing. Please complete it, Kishore. Yeah. Fine. So, but still omega less than omega s. So d delta by dt value was positive. Delta will increase. Delta will increase up to the point where omega equals to omega s occurs. Up to the point where omega equals to omega s occurs. Okay. Whether we are going to touch that omega equals to omega s or not, that depends upon the areas what we have discussed. Let's move back, and I'll tell you here. Just listen. Yeah, see this. First area what we have covered, just observe. First area what we have covered here, that is starting from A to B. Okay, means between delta naught and delta 1 angles. Between delta naught and delta 1, between these two angles. What are the other limits? PS2, mechanical load line, and then electrical power input, that is PE curve. And whatever the intersection between these things, that we are going to call as area. So let us say this is our area. Yeah. So this is the area I'm showing as A1. This is the area I'm showing as A1. Maybe it's a deacceleration area right now. Yeah. Next. See, beyond this point, whatever the area we are going to cover now, that should match with the area A1. By that way, we can say the system is stable or unstable. Okay, could you please tell me what is A2 max available here? What is it A2 max available? This whole area is A2 max. Already we have experienced with equal area criteria many times. Yes or no? This whole area, whatever is available, this is our A2 max. And what is the point which we should not cross? I said this point. This is our X point, right? That's the X point which we should not cross. If you are crossing that one, the system will become unstable. See, A2 max area becomes very, very high compared to A1 area. So definitely the system will be stable. And it won't touch to the point X also. At some point, maybe this I am calling as C, at which we might be getting definitely omega equals to omega s. Definitely we'll get omega equals to omega s. And this point angle, Let me name it as delta 2. Let me name the angle as delta 2. And this is that area we are denoting as A2. This area we are denoting as A2 area, which is exactly matched with the area A1. By that way, the net acceleration will become 0 by reaching to the point C, and we will touch omega equals to omega s. Okay, yeah, let me write that statement. Obviously, Vishnu, very simple. Electrical power is automatically varying due to change in the delta. Yes, that's what I am also saying. Because PE equation is what? P maximum sine delta. That's it. Yeah, let's continue. Let's continue here. So let at the point C, omega equals to omega s was occurred. At that point C, we are touching that omega equals to omega s. Yeah. Let's continue with this. Let's continue. In cases previously X on PS1, E automatically varying. Yeah. Let's continue. So I'll write from that point what we call B to C here. B to C, it's a very simple one to write. From that point B to C, B to C. If you take up the accelerating power PA, electrical power input is P maximum sine delta, which is greater compared to the mechanical load PS2. Greater compared to the mechanical load PS2, and this number is positive. So d omega by dt value was positive. So we have an acceleration. And in that span, of course, omega increases, but omega still less than omega s. If that is the case, if you think about the value d delta by dt, which is omega s minus omega, that number was positive. Delta value was increased. Delta value was increased in that zone. Okay. Delta value was increased in that zone. B to C. Next thing. So at that point C where we are standing, rotor angle is delta 2 we have taken, and omega we touch it to synchronous speed as we said just now. And obviously the value d delta by dt at an angle of delta 2 we are touching to 0. So when the d delta by dt will become 0, in the sense, obviously, integral of PA d delta is equals to 0. Integral of PA d delta is equals to 0, right? So integral of PA d delta equals 0 at what point? Delta 2. So we have to take this integration up to the angle of delta 2. Starting from which angle? Please tell me. Starting from which angle? Delta naught, obviously. Starting from the angle delta naught. So delta naught to delta 2, integral of PA d delta is equals to 0. Now you please divide this integration into two parts. First one is from delta naught to delta 1. Maybe the acceleration we have. Delta 1 to delta 2, we have an acceleration. Okay. So let's move in the next slide to take up the two integrals. Delta naught to delta 1, it is PA d delta plus integral delta 1 to delta 2 integral PA d delta is equals to 0. Yeah, I'm asking one very simple question. If you are solving a problem, listen to me. If you are solving a mathematical problem, Is it required to divide this integral into two parts? Or can we continue with only one integration? Actually, it depends upon the PA equation, how it is. It depends upon how the PA equation will be. See, actually, accelerating power equation is electrical input minus mechanical output. What is electrical input here? P maximum sine delta. What is the mechanical output? PS2. It will be remains the same equation throughout the integration duration, right? Either it is from delta naught to delta 1 or delta 1 to delta 2, that in that integration duration, PA equation will be remains same. So as PA equation remains same, in the problems while you are solving, it's not required to divide this into two integrals. You can go with only one integral here. Okay, but I'm making a small change here. Kindly observe. In the equations what I'm writing. Delta naught to delta 1. What is accelerating power? P maximum sine delta minus PS2 we have written till now. But if you go with the swing equation with respect to delta, this PA will come PS2 minus P maximum sine delta with respect to delta. Next one. Integration starting from delta 1 to delta 2. What is that PA? Same. PS2 minus P maximum sine delta with respect to delta. Please kindly don't confuse. Okay. This integral of PA d delta equation and all we derived from md square delta by dt square equals to mechanical minus electrical. From that equation we have derived this one. Of course, we discussed it in the synchronous motor. We have written accelerating power for the rotor body as electrical input minus mechanical output. That's okay. But as far as swing equation in terms of delta is concerned, you will be getting like that swing equation with respect to delta. If you write, it will be like m d square delta by dt square is equals to mechanical minus electrical. Okay. Yeah. So on that view, I have written in this manner. So the first area you can call it as A1 area. Second area you can call it as A2 area. First area you can call it as A1 area. Second area you can call it as A2 area. Of course, you know A1 plus A2 is equals to 0. And you can write the A2 is equals to minus A1, or you can call magnitude of the A2 area and magnitude of A1 area both are exactly equal. Magnitude of A2 area and magnitude of A1 area both are exactly equal. So can we stop the stability analysis at this point for this case? Can we confirm that the system is stable? Tell me please. Yes, it will be definitely stable, provided that there is no second disturbance on the system. Let me write it. So system is transiently stable. Provided that there is no second disturbance. Provided that there is no second disturbance. But whatever the point we have stopped our study, that is at the point C, point C. That is not the final stable point to be expected. Because why? In the sense, you got omega equals to omega s at the point C, but still accelerating power is non-zero. Means accelerating power is positive. As accelerating power is positive, omega will not stand at omega s continuously. It will start increase further beyond omega s. Okay, that's why the point C is not the final stable point in our expectation. Okay, which will be the final stable point for us? What are the conditions required to be satisfied for a final stable point? What are the conditions required to be satisfied for a final stable point? D omega by dt value 0, d delta by dt value 0. Simultaneously should occur at some location. Yes or no? Both d omega by dt and d delta by dt should become 0 simultaneously at a particular location. That point we can say as final stable point. And after reaching to steady state, whether it is stable or not, in the sense, we should check the value of dp by d delta. dp by similar to the previous case studies what we have discussed. Okay, good. So let's continue with this now. But C is not the final stable point. C is not the final stable point. Final stable point. Done. Next thing. Let's continue. I'll take up the backswing for an extension of our study. Backswing, you write. Backswing for our extension. Simple, very simple. Look here. So at point C, where we said accelerating power is positive value because electrical input is greater compared to the mechanical demand. This is your electrical power input and this is your mechanical demand. So that is positive, right? So accelerating power is positive. So omega, you write like this. From point C onwards, therefore, from point C onwards, omega increases. Omega increases beyond omega s. Omega increases beyond omega s. So as omega greater than omega s occurs, and if you calculate the value of d delta by dt, which is omega s minus omega, that number is negative. As the d delta by dt is negative, yes. D delta by dt is negative. Delta decreases from that angle delta to what we have denoted. Delta will decrease from the angle delta to what we have denoted. Okay, yeah, let me show that here. So delta will be decreasing from delta to in this manner, and swing will fall back and it may make some oscillation and finally it will settle to some point, expecting that as B. What's the reason to say the point B? In the whole swinging, only point B is having PA equals to 0. In the whole swinging, only point B is having PA equals 0. At that point, if omega also becomes omega s, then we can say that point B might be the final stable point to be expected. Okay, fine. Let's continue. I will show the same graph. And I will show that backs. So only one curve we have, that's power angle curve PE. This is sufficient to consider now, right? And we don't know about PS1 right now. We don't know about this PS1 as well as at point A also we don't know right now for time being. And we have only PS2. And this is power axis, all right? Power axis. Now let's show this. I have to show that forward swing also, just for the sake of reference, as I said, showing the forward swing also. Okay. Observe here. Next. Look here, the point C I am identifying here. This is that point C where we have stopped the analysis. And at this point C, angle is how much? Delta 2. Angle is delta 2 at this point C. Now, as we have explained just now, delta angle will decrease from delta 2. Fine. So as angle is decreasing from delta 2, electrical power input will decrease like this. Electrical power is decreasing, that's okay, but still it is greater compared to mechanical power input. So accelerating power is still positive. Omega value will increase in that particular zone. Omega value will increase, and not only that, it is greater compared to synchronous speed. And if you touch to this point, so-called B, and maybe the same angle which we said as delta 2, accelerating power is 0, but omega is more than omega s at that location. But omega is greater than omega s at that particular location. Because of that, d delta by dt is still negative. delta will decrease below the value of delta 1. Delta will decrease below the value of delta 1 like this. Because of that, electrical power input will fall down. Electrical power input will fall down. And electrical power input is becoming less compared to mechanical input. Because of that, mechanical load. Because of that, omega starts decrease in this zone, but still omega may be greater than omega s. Right? And at what point we are going to touch that omega equals to omega s means, again it may touch to the point A. Again, it may touch to the point A. And if you don't consider damping, I'm saying, if you don't consider the damping, it may touch to the point A, right? At which you might be having omega equals to omega s. I think all of you getting these points, what I said. Very simple thing. Very simple thing. Many times we discuss no. Yeah. So let me write these things very quickly because this is a bit different from the previous case studies we have taken up. That's why I will write these things a little bit. Yeah, please draw this one quickly. To B, point C to B. So if you take accelerating power PA, accelerating power PA, Just I will write quickly. I don't write in detail. I don't write in detail. Okay, just to take C to B like this. Accelerating power, it is input minus output, that is positive, right? Electrical input is more compared to mechanical. Omega value was increasing in that zone, omega greater than omega s. And you know the value d delta by dt, omega s minus omega, that is negative, delta value was decreased in that zone. Keep it aside. At that point B, at that point B, see, obviously we will be touching to the maximum speed at this location, right? So omega max, accelerating power is 0, omega touch it to omega max, and not only that, that omega is greater compared to omega s. And but you know, at this point B, d delta by dt number still negative, still negative. So from point B onwards, from that B onwards, from that point B onwards, what will happen is, as d delta by dt is negative, delta will decrease. Delta will decrease from delta 1. Delta decreases from delta 1. So, and PA becomes negative. PA becomes negative. So, as PA is becoming negative, omega also decreasing from omega max. Omega also decreasing from omega max. Okay? Yeah, done. Next. Omega also decreasing from omega max. Now, you write it from what we call B to A, B to A. From that point B to point A, you can write accelerating power is negative. Accelerating power is negative. D omega by dt value was negative. Omega value was decreasing, but still it is greater compared to synchronous speed. D delta by dt negative, delta value was decreasing, we can say. Delta value was decreasing, we can say. Fine. Next, after touching to that point A, after touching to that point A, at that point A, you know, I'll say at that point A, omega is equals to omega s, but accelerating power value still negative. Accelerating power value still negative. And from A onwards, you know, as PA is negative, definitely omega decreases and omega less than omega s occurs. Omega less than omega s occurs. And d delta by dt number is negative. So, sorry, positive. Delta starts increasing now. Delta starts increasing, we can say. Okay, done. So, I can write the final comments now by showing these areas a bit quickly. This is one area, you can call it as A3 area. This is the other area, I'm calling this as A4 area. A3 area, A4 area. Getting all of you? Yeah. A3 area, A4 area. And you can say simply the rotor will be swinging continuously between these 2 points. These 2 points, so called A and C, A and C. And if damping is considered, and finally both points will be coincide the point B. Yeah, please write it quickly. Please write it quickly. So I can say from this, rotor will be continuously swinging between points A and B, points A and C, right? A and C, at which, you know, the speed is equals to synchronous speed. A and C, right? So you write at the point A, we have omega is equals to omega s. At C also, we have omega is equals to omega s. At that point A and point C. Definitely A2 and A3 also equal. Definitely A2 and A3 also equal. Sure. A3 plus A4 is equals to 0. and you write magnitude of the A4 value is equals to magnitude of A. Yeah, fine. So let's say if damping is considered in the next slide. If damping is considered. Damping is considered. Consider. Yeah, please complete it quickly. If damping is considered, what will happen? Points A and points A and C will come close together. Will come close together. Swing by swing. Swing by swing with respect to time. Swing by swing with respect to time. And finally, inclined onto the point B. Inclined onto the point B. Okay. And how is the speed at B? How is the speed at that point B? Look here. How is the speed at B? So in the forward swing, if you are going from A to C, we are touching omega minimum value. And in the back swing, we are touching maximum. Again, minimum, maximum. The speed at the point B continuously changing between omega minimum and omega maximum. And finally, we'll touch omega equals to omega s at some time. Okay? Yeah. So I can write speed at point B will vary between omega minimum and omega maximum. And finally, omega equals to omega s occurs. And finally, we will be getting omega equals to omega s. Next thing. So finally, at the point B, if you talk, finally at B, already we are saying omega equals to omega s means d delta by dt number is 0. And always at the point you observe that electrical power input, mechanical load are exactly matched. Accelerating power is 0. So you can say d omega by dt is 0. Once after saying these two are reaching to 0, we will say the system reached to steady state. System reaches to steady state. System reaches to steady state. Okay. Yeah. So next thing. How is the angle at that location? Kindly look there. How is the angle at that location? Yeah. How is the angle? Delta 1, na? What is the angle delta 1? Sine inverse of PS2 by P maximum. Sine inverse of PS2 by P maximum. So finally, angle at that location, delta 1 is nothing but sine inverse of PS2 by P maximum. Sine inverse of PS2 by P maximum. Okay, fine. Now quickly take up that delta versus time curve, swing curve, and then omega versus time curve also. Delta versus time, omega versus time. After that, we discuss about the unstable case. Yeah. So you draw delta versus time curve quickly. Delta versus time curve. So this is a time axis we have. And this was a delta axis. Time axis, delta axis. And you consider this time as T0. T0. And up to the time T0, you have an angle of delta naught here. Up to the time T0, we have an angle of delta naught. Again, as I said you earlier, we have to think about only these four things. What is the initial rotor angle? What is the maximum angle seen by the rotor? What is the minimum angle seen by the rotor? How is the final stable angle? These things only we should consider. Delta naught, delta maximum, delta minimum, as well as a final stable angle we can see. Okay, what is delta max here? What is delta max in this swinging? That is delta 2 is a delta maximum angle. Okay, delta max is delta 2. What is delta minimum? That will be delta naught only. Delta minimum value will be delta naught. What is delta f? Delta 1, which is greater than delta naught. Which is greater than delta naught. Okay, see this. Up to this point, time T naught, we have this angle as delta naught. Let me show that line. Let me show this line, delta naught line, something like this. And maximum angle is delta 2. Let me show that in this manner, delta 2. Maximum angle. And final stable angle is delta 1. I'm showing that here. This is delta 1. Kindly observe. So this is the angle I'm showing the delta 2. And this is the angle delta 1, I will say. So simply, rotor angle will increase starting from delta naught and reaching to maximum value delta 2, comes back to delta naught, and it will vary, and finally you get final stable angle as delta 1. Okay, yeah. So let's move. This is an angle variation to be expected. This is an angle variation to be expected. Something like this you can observe. Right? So finally, you are going to get this angle as delta 1. That's a final stable angle to be expected. Final stable angle to be expected. Yeah. Machines are designed with certain damping. Certain damping may not be very high. May not be very high damping. Those are designed with certain damping to make up the system stable, reaching to steady state quickly after creating the disturbance. Okay, see, this is one doubt many of the people might be getting. Sir, in case of synchronous motor, your rotor angle is negative. In case of synchronous motor, your rotor angle is negative. Then why you have shown here positive angle? Why you have shown here positive angle? I'll tell you, very simple reason, very simple reason. This is a system we have considered, right? This is a synchronous motor. And we have the shaft, right? And this voltage is mod V at an angle minus delta. Internal voltage is mod V at an angle 0. Yeah, please tell me. Very simple thing. Just answer to my question what I am asking you. How is your internal EMF of synchronous motor with respect to infinite bus? How is the internal EMF of synchronous motor with respect to infinite bus? It will be in lagging. Minus delta angle I have shown you. Minus delta angle I have shown you. How is delta? Is it positive or negative? Minus delta is okay. How is delta? Is it positive or negative? Tell me please. That will be positive. Delta will be positive because already you kept a minus sign, right? So I have shown the delta as positive. So negative of this angle is an internal EMF angle of the motor. Okay, for example, I will show in the next slide. For example, same thing, it's an infinite bus bar connected to synchronous motor. Okay, and this is an infinite bus voltage mod V at an angle 0. Internal EMF mod V at an angle delta plus delta I have shown you. Plus delta. How is that delta now? Is it positive or negative? Anybody? How is the delta in the second case? It's the second case you take if you want. And this is the first case. Yeah, tell me. That will be negative, right? That will be negative. And in this case, if you want to draw the delta versus time, we should show that in the negative region. Okay, in this case, delta is a negative angle. Delta is a negative angle. So simply, I will show that angle variation with respect to time. Right? It's a delta angle with respect to time. Delta angle with respect to time, and it's a time t naught. T naught. Up to the time t naught, we have an angle of delta naught here. Up to the time t naught, we have an angle of delta naught. Okay, then simply the delta will come down up to delta 2, reaches back to delta naught and makes some oscillation, and finally settles at delta 1 as it is what we have discussed earlier. Okay, so this is the angle delta naught. I will show minimum angle. Okay, maximum angle touching is delta 2, something like this. And in between that, we have an angle of delta 1. Okay, so this angle will be varying something like this and touching to this. And it will make some oscillations continuously like this. And finally, it will settle to this angle. That is delta. This is delta 2 negative angle, and this is a delta 1 negative angle. Delta 2, delta 1 negative angles. Okay, once after completion, please try to draw omega versus time also. Please try to draw that omega versus time. Omega versus time. Speed with respect to time. Please kindly draw the speed versus time. Yeah. So omega versus time we have. Speed with respect to time. Speed with respect to time. So I will be showing time axis here first. This is the time axis. And I'm showing omega axis here. Omega axis. And this is a time t naught. T naught. Up to the time t naught, we have the speed as synchronous speed. Omega is constant. I'm showing. This is a synchronous speed. Omega is. Yeah. Yeah. Look here. And this is a point A. This is a point A. Yeah. This is a point A where we are standing, at which omega equals to omega s. Omega equals to omega s. Starting from the point A to B, point A to point B, omega value was decreasing. Omega value was decreasing, and it will be reaching to minimum speed. And from B to C, omega value was increasing, and it will be touching back to synchronous. Means I should say starting from this point A to B, speed value was decreasing and reaching to minimum. And then from B onwards, it will increase, touching to synchronous. Like this, you will be getting that variation, right? You'll be getting the variation in this manner. Next one. Look, starting from C. Look here, starting from C. C to B, omega touching to maximum. B to A comes back to synchronous. So C to B, it will be touching to maximum speed, and then it will touch to the point A at which you get omega equals to omega. So simply that omega versus time variation will be continuously changing in that manner. And at the point B, continuously we have maximum and minimum speeds, continuously between maximum and minimum, and finally you will touch omega equals to omega s at that location. So it will be changing in between omega max and omega min, and finally you will get omega equals to omega. And this is a point B we are showing. Point B we are showing like this. And finally you will get omega equals to omega at that location. Yeah, you can call this as hunting also. Omega versus time, and then delta versus time. Fine. Next thing. So I'll say in the next case, unstable case we'll discuss. As it is, we have said earlier, but we will show the delta versus time and omega versus time, how the change we are going to get compared to the generator case. Yeah, look here. Same graph I will show here. I'll draw a new one. Just observe. It's a delta axis we have, and it's a power axis. Power axis and delta axis like this. Power axis, and this was of delta axis. Okay, first electrical power, which is P maximum sine delta curve. Electrical power, it is P maximum sine delta curve, something like this you may get. Okay, so this is a P maximum value we have. P maximum sine delta. Next, the initial mechanical load is PS1. I'm showing that initial mechanical load at this place. This is the initial mechanical load PS1. All of a sudden, this mechanical load value was increased to a number PS2. Let me show initial operating point and all quickly. We have discussed it till now. This is a point angle of delta naught, and omega is equals to omega s. Omega equals to omega s. And as we said, all of a sudden, this mechanical load was increased to a number PS2. Mechanical load value was increased to a number PS2, something like this. Okay, yeah, done. Next thing. So as we said earlier, at point A, if you are standing, your mechanical output is more, but electrical input is less. Because of that, accelerating power is negative. d omega by dt negative. Omega starts decreasing from omega s. If that is the case, delta will start increase beyond delta naught. So operating point will move on this power angle curve, something like this. So omega value was decreasing, and that is less compared to omega s. And we will be touching to this point where accelerating power is equals to 0. That's a point B, we can say. Point B, accelerating power is equals to 0. And this point I am calling as an angle delta. Angle as delta. Now, simple. Just observe. This is one area we have covered till now. A1. That's one area we have covered till now. That is A1. And this whole area remaining what we have, that is A2 max. This whole area what we have here, A2 max. All of you getting this one? A2 max. Okay, very simple. Just look here. For example, from B onwards, operating point is moving something like this, and omega starts increase, but still omega will be less than omega s. Because of the d delta by dt is positive, delta will continue to increase. So if you are tracing something like this continuously, omega is increasing and omega less than omega s, d delta by dt is positive, delta will continue to increase. See, even after touching to this point, maybe x, you can say, even after touching to this point x, if you are unable to touch omega equals to omega s, or if you are unable to get omega equals to omega s, still after touching to the point x, if you get omega less than omega s, d delta by dt is still positive. Delta will continue to increase beyond this angle delta x. Beyond that angle delta x. And operating point will move down like this. Operating point will move down in that manner. See, if the operating point is moving down like that, we are entering into which region? Deceleration region, where electrical input is falling down to the value of mechanical load. So because of that, omega will start decrease now. Already omega less than omega s, and omega further decreasing means omega less than omega s only, d delta by dt is positive, delta will continue to increase, and operating point will come down in this manner continuously, and omega continue to decrease, and that is less compared to synchronous speed, and d delta by dt is positive, and finally we will get zero speed. Finally, we are going to touch omega equals to 0, and we will confirm that the system will be unstable. We'll confirm that the system will be unstable. All of you getting this point? Please tell me once. All of you getting this? Yeah. Now, can you please draw that delta versus time curve for this unstable case, as well as omega versus time curve for this unstable case? Draw this one. Make it quick, please. So if you take up the delta versus time curve, it's a time axis. It is a delta axis, right? Delta versus time curve, and it's a time t naught, up to which we have an angle of delta naught, as we said earlier, up to which we have an angle of delta naught. And starting from this time t naught, so-called angle delta naught, angle will continue to increase. That's it. If it's an unstable case, angle will continue to increase beyond delta x. So you will get that simple delta versus time variation like this. How is omega versus time now? How is that omega versus time? It is a time axis. Yeah, kindly observe this omega versus time for the unstable case. Omega versus time for the unstable case. And it was a time t naught. Time t naught. Just look here. Just look here. up to the time t naught, we have the speed as synchronous speed, omega s. We have the speed as synchronous speed, omega s. Let me show that line, omega s line, for reference sake, for the reference sake. Next, look here. You take up this is point A, take up this as point A. Next. Starting from point A to point B, omega decreasing. A to B, omega value was decreasing. So variation in the speed, something like this you can experience. This is a point B, decreasing. From B to X speed is increasing. It will attempt to touch synchronous. It will attempt to touch the synchronous speed, but it's unable. And finally, it will fall down to 0. Following all of you. So it will decrease first and it will try to catch up the synchronous speed, but it's unable to touch that. And from that point onwards, it will start decreasing and finally the speed value will become 0 like this. Finally, the value of omega will fall down to 0 something. And this is a point X we are calling. That's the point X we are calling, where the point X will have a speed less than synchronous speed. Less than synchronous speed. Okay? This is omega versus time. Non-stabilities. Okay, for example, I'll copy this curve. Some little modification. I'll discuss about this one. I'll draw new issue. I'm taking up in the next slide. Next slide. Just have a look here. So I'm showing a infinite bus connected to some network here, and it is a synchronous motor, and it's a mechanical load. Okay, let me show that delta versus time. It's a time axis. Sorry, not delta versus time. It's a power angle curve we are plotting. P versus delta power angle curve. Just look here, P versus delta. So this is a power angle curve we have. PS1, PS2, mechanical input, mechanical load in the initial condition, mechanical load after making that increment. Just observe. Observe the words what I am saying. Just listen. It is PS1. So this is the point A where we have delta naught. And we'll get omega is equals to omega s. Omega is equals to omega s. Yeah. Next, look here. All of a sudden, this mechanical load was increased from PS1 to PS2, as we said. So it was increased from PS1 to PS2. PS2, something like this. Listen to this. And starting from this point A, and it will reach to this point, so-called B. And then, in this zone, omega value was decreasing, and here, omega value was increasing. For example, if you are getting omega equals to omega s exactly at this point X, let us say, if you are getting omega equals to omega s exactly at this point X, the angle is delta X here. Angle is delta X, right? And already we have divided these areas now. So this area we are naming it as A2 max area, and this area we are naming it as A1 area. Okay, so first area we are calling A1, second area we are naming it as A2 max. Okay, done. Next thing. Next thing, kindly observe. So definitely you will get A2 max and A1 values as exactly equal. Or else you write A1 plus A2 max is equals to 0. and you write A2 max value exactly equals to modulus of A. What we name this PS2? Anybody? What we name the PS2? What we name that PS2? Anybody tell me please? That is going to be called as transient stability limit. That PS2 what we have here, not PS1, not the value of PS1, PS2 now, PS2. That is going to be called as transient stability limit in this particular diagram. Transient stability limit. Not only that, what is the maximum change or what is the maximum addition of load accepted by the system? Maximum addition of load or maximum and sudden increment in the load accepted by system, that is nothing but PS2 minus PS1. Okay, with an initial condition of PS1 I am talking. With the initial condition of PS1 we are talking. Okay, so I'll write maximum and sudden increment. Sudden increment in mechanical load accepted by the system without losing synchronism. Accepted by the system without losing synchronism is equals to PS2 minus PS1. Maximum and sudden increment in the mechanical load accepted by the system without losing synchronism, that is PS2 minus PS1. Yeah, done. So I think all of you getting this. Yeah, so next we'll do 1 or 2 problems on this case study quickly. Then we will discuss about methods to improve the transient stability of the system. How to improve the transient stability of the system means what are the various measures we have to take up in order to maintain good stability for the system after creating the large disturbance. Okay, yeah. So I'll take up this problem, very simple problem. Just look here, I'm writing the problem. A synchronous motor connected to infinite bus bar. A synchronous motor connected to infinite bus bar. Synchronous motor connected to infinite bus bar having a maximum power transfer capacity of network. Maximum power transfer capacity of network. Transfer capacity of network as maximum power transfer capacity of network as 4 per unit. 4 per unit. The initial mechanical load, right? The mechanical load on motor shaft, on the motor shaft is 2 per unit. Mechanical load on the motor shaft is 2 per unit. Next thing, a sudden increment in mechanical load was made. A sudden increment in the mechanical load was made such that the maximum angle seen by the rotor is seen by the rotor is 90 degrees. The maximum angle seen by the rotor is 90 degrees. Okay, the system is stable. To stop, find the new electrical power flow. new electrical power flow after reaching to steady state. After reaching to steady state. Find the new electrical power flow after reaching to steady state. Okay, so attempt to do this problem. Kindly look at the data what I have provided. We have a synchronous motor connected to infinite bus bar, and that network is having a maximum power transfer capacity of 4 per unit. Okay, mechanical load on the motor shaft is 2 per unit. A sudden increment in the mechanical load was made such that the maximum angle seen by the rotor is 90 degree. What is 90 degree? Can we call this as delta x? Yeah, I want to tell the meaning of this maximum angle seen here. That's why I am discussing about this problem. Can we call this angle as delta x, 90 degree? May not be. May not be. It may not be what we call delta x, right? See, actually, in the previous graphs you have shown, just observe here. Just observe in these graphs. In these graphs, what is the maximum angle seen by the rotor? What's the maximum angle seen by the rotor in these graphs? It will be delta 2, right? It's not delta x angle. Maximum angle seen by the rotor is delta 2. That's the angle at which you touch the omega equals to omega s. That's not the angle of delta x. What do you mean by delta x here? Delta x is the maximum angle seen by the rotor before which we should get omega equals to omega s. Means before touching delta x angle, we should get omega equals to omega s. That is the point x we have shown. Okay, so it is some angle 90 degree. Whether it is equal to delta x or not equals to delta x, it is immaterial for me. But one thing what I can say is, after touching to 90 degree, if you are getting, sorry, if you are saying that is a maximum angle, obviously at 90 degree angle, d delta by dt value is equals to 0. So integral of PA d delta is equal to 0. Up to which angle? 90 degree we should take. Starting from which angle? Initial angle. That we have to calculate from the data given. Okay, yeah. So let's continue. Let's continue like this. So we have a network, infinite bus bar, and this is a power network we have, and it is synchronous motor. Synchronous motor. Maximum power transfer capacity of network is 4 per unit. 4 per unit. Please tell me, what is that mechanical load on the motor shaft? 2 per unit. That's the value of PS1. Initial mechanical load on the motor shaft. Initial mechanical load PS1 is equals to 2 per unit. Okay, done. A sudden increment in the mechanical load was made such that the maximum angle seen by the rotor is 90 degrees. Yeah, let me write. Maximum angle seen by, let me write first delta naught. What is the initial rotor angle delta naught? Sine inverse of PS1 by P maximum. I think all of you comfortable with this formula. We discussed in the analysis earlier. So it is 2 by 4 sine inverse. That means it will be 30 degrees. Now, a sudden increment in the mechanical load was made. Sudden increment in mechanical load was made. Load was made to a value PS2. Suddenly, mechanical load was increased from the value PS1 to PS2. Okay, next thing. Next thing. Maximum angle seen by the rotor is is equals to 90 degrees. 90 degrees. Okay. Now, simply you write here d delta by dt at an angle of 90 degree is equals to 0. That you can say. Means you write integral PA d delta is equals to 0. Up to which angle you should take? 90 degree. Starting from which angle? 30. Starting from 30 degree to 90 degree, we should say integral of PA d delta is equals to 0. Whether the PA equation is remains same in the whole duration of angle variation, because P maximum is remains same, na? P max equation was remains, sorry, P max value was remains same. So that equation will be simply PS2 minus P maximum sine delta. That's it. Okay. So you can write now integral 30 degrees to 90 degree PS2 minus P maximum sine delta with respect to delta is equals to 0. Okay, you simply do that integration and substitute the angles in the ultimately what you have to calculate? What you have to calculate? PS2 value only, right? What is asking? The system is stable. Okay. Find the new electrical power flow after reaching to steady state. That is nothing but PS2 value. That's a mechanical load on the shaft of the motor. The same amount of electrical power will be flowing in the network. Okay. Yeah. So I'll write this PS2 into, we have this 90 degree minus 30 degree, but you should keep this in radian. So pi multiply with pi by 180 plus P max into cos 90 degree minus cos 30 degrees. Cos 90 degree minus cos 30 degree, that will be equals to 0. Okay. What is PS2 number? That we have to calculate as we said. That we have to calculate as we said. And P max value already we know it is 4. It is 4. Okay. You do this calculation quickly. I'll write in the next slide. PS2 is equals to simply minus P maximum is 4 cos 90 minus cos 30 whole by it is 90 minus 30 means 60 degree into pi by 180. Pi by 180. You please calculate this number how much? How much is this PS2? Now if you are saying that is 3.307. 3.307 per unit. So after reaching to steady state, this is the amount of electrical power flowing in the network. So therefore, after reaching to steady state, electrical power flow is equals to 3.307 per unit. 3.307 per unit. So I think all of you getting this? Done? So let's take up one more problem quickly. Next question I am taking up. Yeah, look here. So an alternator connected to synchronous motor through a network of reactances. The alternator is rated for look this. Okay. The alternator is rated for 100 MVA, 50 Hz, H equals to 6 seconds. And the motor is rated for 80 MVA, 50 Hz, H equals to 5 seconds. The initial power transferred from alternator to motor is 80 megawatt. Initial power flow in the network is 80 megawatt is saying. Next. A three-phase fault occurred at some location in the network suddenly reduced the electrical power transfer to a number 30 megawatt. Electrical power flow in the network suddenly decreased to a value 30 megawatt from 80. Initial value 80, now it is 30. Okay. The acceleration of the rotor angular difference between the alternator and synchronous motor at the instant of the fault is dash electrical degree by second square. At the instant of the fault, how much is the rotor angular acceleration? How much is the rotor angular acceleration? Yeah. Attempt to get this. See, rotor angular acceleration means we have to find out d square delta by dt square. That's okay. But what is a delta? The angular difference between the two machines. Between generator and motor, we have to consider. Okay. What is the formula for d square delta by dt square? PA by M. PA by M. What is accelerating power? First of all, what you should do is we should convert these two machines into a single machine. First, to convert these two machines into single machine. Then you take up the fault, whatever is said, take up the change in the electrical power, and then you calculate the d square delta by dt square. Clear, right? So let's say in the next slide, the solution. Just observe first. Yeah. See, this is a two machine system we have. It's a generator connected to power network, something like this network. And this is a synchronous motor, we say. Synchronous motor. Yeah. First of all, you take up the ratings of these machines. First one, 100 MVA, 50 Hertz. 100 MVA, 50 Hertz. And how much is the H value here? What's the H value? That will be 6 seconds. Okay, what is the second machine? 80 MVA, 50 Hertz, 5 seconds. 80 MVA, 50 Hertz, 5 seconds. H value was 5 seconds. And we have to convert these two machines into a single machine, something like this. We have to convert these two machines into a single machine, something like this. Clear? Now please tell me, what is that M equivalent of this single machine system? How is the M equivalent of that single machine system? Anybody tell me, please? 1 by M equivalent equals to 1 by M1 plus 1 by M2? Yes or no? Yes. 1 by G equivalent H equivalent is equals to 1 by G1 H1 plus 1 by G2 H2. What is G equivalent value? What is the G equivalent value? Anybody know about it? We don't know. So you simply calculate G equivalent into H equivalent. So called kinetic energy you calculate. After that we go for M equivalent value. Okay. One more thing, I have said the formula directly to you. First tell me whether these two machines are swinging or not swinging. Whether these two machines are swinging or not swinging. Definitely not swinging. One is a generator, other one is a motor, not swinging together. Okay. So as machines are not swinging together, first you write this statement. As machines are not swinging together, So you write 1 by G equivalent H equivalent is equals to 1 by G1 H1 plus 1 by G2 H2. Yeah, you please substitute these numbers. G1 H1 100 into 6, 1 by G2 H2 80 into 5. Okay, from this you please calculate this G equivalent into H equivalent quickly. How much will be the value of G equivalent into H equivalent? Calculate this number, please tell me. 240. You are getting this number as 240 megajoules. Units will be megajoules. All of you getting this? Yeah, good. 240 megajoules. Now, M equivalent value we have to calculate. We'll do that. First, you have to take up the d square delta by dt square. Let us say this is delta 1 angle, is having an angle of delta 2. Then what is the resultant angle of this one? Delta 1 minus delta 2, right? Delta 1 minus delta 2. So you can write now M equivalent into d square delta 1 2 by dt square is equals to accelerating power PA. What is that accelerating power means? This is the mechanical input PS and electrical power flow is P. Okay. Initially he said power flow in the network is 80 megawatt. Means that initial power flow what you have 80 itself is a mechanical input you should consider. Clear? I will write. Initial electrical power flow is equal to 80 megawatt. That implies you can write mechanical input. PS value was 80 megawatt. PS value was 80 megawatt. Okay, now suddenly electrical power flow in the network was reduced to 30 megawatt. Reduced by or reduced to? Look here. Reduced the electrical power transfer to 30 megawatt. Fine. So due to disturbance, electrical power reduced to a number 30 megawatts. Then what will be the value of accelerating power? You should say mechanical input minus electrical output. So 80 minus 30, that will come to be 50 megawatt. So accelerating power PA is equals to PS minus PE. So it will be 80 minus 30. So it will be 50 megawatt obviously. 80 minus 50, that will be 80 minus 30, that will be 50 megawatt. Yeah, next thing. Let's continue. So PA equals to 50. Now you write that d square delta 1 2 by dt square. D square delta 1 2 by dt square formula. Rotor angular acceleration. It is accelerating power by angular momentum m. What is that angular momentum formula? What is the formula for angular momentum? We should keep in electrical degree. So where m is equals to, in terms of electrical degree, it will be G equivalent into H equivalent by 180 F second square, megajoule second by electrical degree. Megajoule second by electrical degrees. G equivalent into H equivalent by 180 F megajoule second by electrical degree. So what is the G equivalent into H equivalent value? How much is the G equivalent into H equivalent? 240 by 180 into frequency is 50. So you get this like megajoule second by electrical degrees. Megajoule second by electrical degrees. Now you calculate the d square delta 1 2 by dt square value. D square delta 1 2 by dt square value. Accelerating power. How much is that accelerating power? 50 mega by 240 by 180 into 50. Yeah. So this will come to be second square by electrical degree. Electrical degree by second square. Will come to be electrical degree by second square. Yeah, please calculate this number. How much? 1875. 1875 electrical degree by second square. Electrical degree by second square. 1875. Okay. So let's move to the next topic, that is methods to improve the transient stability of system. Methods to improve transient stability of system. Next heading. So do we aware of that PS2 minus PS1 limit during power factor improvement of synchronous motor? Ankur, you asked me, you please elaborate your doubt in doubt session once. Okay. You are linking the power factor with the limit and all. Please ask me in doubt session. I will explain. Yeah. So next heading I am taking up now. Methods to improve. Methods to improve transient stability of the system. Transient stability of the system. Methods to improve the transient stability of the system. Okay. Listen here. See, as we said, in case of steady state stability of system, we said we have only one method to improve steady state stability, that is making the value of dP by d delta. dP by d delta, so-called synchronizing power coefficient as high as possible. Making synchronizing power coefficient value as high as possible. That's the only one method we said in case of improving the steady state stability of system. But improving transient stability of system means, again, I would say only one method, that is maintaining that rotor acceleration as low as possible. are maintaining the d square theta by dt square number as low as possible, or d square delta by dt square number. First of all, I will write that d omega by dt in case of generator. I'm talking only in the view of generator now. D omega by dt equals to d square theta by dt square equals to d square delta by dt square is equals to accelerating power by m. Okay, what is accelerating power equation here? Mechanical input to the generator, I'm talking in the view of generator, minus electrical power is P maximum sine delta. P maximum sine delta. PS minus P maximum sine delta. Okay, let me tell you. See, maintaining good transient stability is nothing but maintaining the d omega by dt, d square theta by dt square, d square delta by dt square as low as possible. First, you write that statement. Maintaining good transient stability means making d square theta by dt square as very low. Making the value of d square theta by dt square as very, very low. Okay, done. Next. First method I am going to tell you to make the d square theta by dt square as very low. First and foremost method is making this m value very high. Means we have to design the machine with a high angular momentum. Design machine with high angular momentum. This is one technique. Other technique is keep the power stations very close together. Keep the power stations very, very close together and connect to the same bus bar. Means you have to keep your power generating station geographically very close and connected to the same bus bar. Makes the machines swing together. Obviously, the overall m value or m equivalent value will rise up and system stability will be definitely improved. Okay, so locate the machines. Second technique here. Locate the machines very close together. Such that machines will swing. Machines will be swinging. So m equivalent value will be high. Because of that high value of m equivalent, definitely d square theta by dt square will be less and system stability is going to be improved. Yeah, please complete it quickly. So I will move to the second method. In the way of mechanical, I will discuss. Second method also I am going to say in the way of mechanical. Okay, actually we got this swing equation as d square theta by dt square equals to Pa by m by neglecting damping. If damping is also considered, how is that? That we'll think now. Okay, yeah, let's see. Number 2, with damping, if you write up that swing equation, is m d square theta by dt square plus d into d theta by dt is equals to accelerating power. Clear? And you take the d into d theta by dt to the other side. And what you will get this acceleration d square theta by dt square value? It will come to be accelerating power minus d into d theta by dt by m. Accelerating power minus d into d theta by dt by m. Tell me now, what's the technique to say or to have this d square theta by dt square as low now? How to make the d square theta by dt square as low? Making the damping as very high. If you provide more damping for the machine, this overall value will be high, and that makes this whole number as low. D square theta by dt square as low, we can say. Okay, so I can write now. So if system is having high damping, definitely we can say transient stability of system will be improved. TS I am writing simply transient stability. Transient stability of the system will be definitely improved. Okay. Next. How to maintain that high damping now? The machine to the generator or motor, whatever it is. How to maintain high damping? High damping will be created by which elements? Damper bars. Keeping damper bars on the rotor pole faces. Keeping damper bars on the rotor pole faces is one technique. And other technique is connecting a large flywheel. Connecting a large flywheel to the rotor shaft. To the rotor shaft. Connecting flywheel to the rotor shaft. So these are the techniques to have high damping. High damping created by damper bars connecting a flywheel to the rotor shaft. Done. Next. Third method we are going to say. Third one. I'm talking only in the view of generator. Maybe with respect to fault, you can treat. Maybe with respect to fault. Look here. See, d square theta by dt square equals to accelerating power by m. D square theta by dt square equals to accelerating power by m. See, if you are capable to maintain that accelerating power value as low as possible, if you are capable to make the accelerating power value as low as possible, then definitely d square theta by dt square is low and system stability will be definitely improved. How to maintain that accelerating power as low? Very simple. For example, as we have discussed earlier, this is one system. We have generator and we have two transmission line network, and this is that infinite bus bar. Okay, some breakers we have here. Breakers, very simple technique, and this is a mechanical input PS. Observe, we have a short circuit fault at some location. Because of the short circuit fault, electrical power flow was falling down. That we know already. Electrical power flow value is falling down. That we have discussed already, right? But whenever that electrical power was falling down, we have a difference PS minus PE created. That's what we are saying accelerating power many times. That's what we are calling as accelerating power, PS minus PE. Now, the thing is, already we discussed this, but still I am repeating. We have one frequency sensor. Whenever the frequency sensor senses that high frequency because of speed increment, whenever it senses that high frequency, what it will do? It will give a command for the speed governor mechanism. And as and when it's giving a command for speed governor mechanism, what it will try to do is always, it will try to maintain the mechanical input value to be equal to electrical output by adjusting the valve. But for the simplicity's sake, in the analysis, in the assumptions of the transient stability analysis itself, we said that we are avoiding the speed governor action. Means we are deactivating the speed governor action. Now you please tell me, if speed governor action is there, then what it will do? It will try to control the value of PS to match with PE. In that sense, definitely net accelerating power during disturbance will come down. Definitely d square theta by dt square will be less and system stability is going to be improved. So if you go with a fast acting speed governor mechanism, definitely we can say the system stability is going to be improved. Yeah, all of you understood this? But again, don't ask me, sir, earlier you said you have neglected it. We have neglected in our theoretical study. But practically speaking, if speed governor is there, if you consider it, then definitely the system stability will be good as compared to deactivation of speed governor mechanism. Clear? Right. So I'm writing the statement now. So by using fast acting speed governor mechanism. Fast acting speed governor mechanism. PS will be controlled. PS will be controlled quickly according to PE variations. According to PE variation. That implies PA will reduce. PA will reduce. That implies transient stability of system will be improved. Right. So this is a method to improve the transient stability. One thing we said, fast acting speed governor mechanism. Fourth one, just observe here. Just observe. See, fault occurred at this place. Definitely, terminal voltage will decrease or falls down. Terminal voltage will fall down. And we have some voltage sensor at this place now. We have some sort of voltage sensor at that place. Okay, whenever that voltage is falling down, this voltage sensor will sense that low voltage. Voltage sensor is going to sense that low voltage. Whenever it is sensing that low voltage, it will give a command for automatic voltage regulator. It will give a command for the automatic voltage regulator, and that automatic voltage regulator will try to correct the excitation. Will try to correct the excitation or induced EMF in the machine in such a way that terminal voltage is going to be maintained as rated value. In such a way that terminal voltage is going to be maintained as rated value. All of you getting my words? Now, as a terminal voltage is falling down, to maintain the terminal voltage to the required number, what should happen to the induced EMF value? Tell me please. What should happen to the induced EMF value? Definitely it is going to be increased. Definitely it's going to be increased by means of the automatic voltage regulator mechanism. So in that sense, we can expect that maximum power transfer capacity of network is going to be increased. Maybe you can say during fault, P maximum will increase. This P maximum 2 will go high. Because of that, I have mentioned already in the case studies we have said, definitely system stability is going to be improved. Means by using fast acting automatic voltage regulator, system stability is going to be definitely improved. Right? So I can say in the next slide, by using fast acting automatic voltage regulator mechanism, MODI induced EMF value will increase during disturbance. That implies system stability will be improved, or transient stability of system will be improved. Transient stability will be improved. So it's another assumption we made in the transient stability analysis. Deactivating the speed governor mechanism, we have said. Deactivating the speed governor mechanism, we said. Automatic voltage regulator. Pujar, already we discussed about this one. Automatic voltage regulator and all in the assumptions. Okay. Fast acting AVR mechanism. Definitely E value will be increased so that maximum power transfer capacity will increase. Right here if you want. Pmax2 will increase during disturbance. Then we can say transient stability of the system will be definitely improved. Next one. Next one you observe. Next one. Fifth one. Just have a look here. So we are concentrating on the accelerating power right now, means in the view of the electrical power. In the view of electrical. PS minus P maximum sine delta. This we are going to concentrate. See, for example, this is one alternator. Just observe my words, what I am saying. Alternator. And it is some mechanical input. And this is star grounded. I'll take it as case number 1 for time. Solidly grounded system. Solidly grounded. And it is RYB phases. Initially, whatever the mechanical input we are giving, electrical power output, PR, PY, PV. Summation of these three powers, PR plus PY plus PV, this summation and PS value exactly equal. Mechanical input value, electrical power output, three-phase electrical power output, PR plus PY plus PV. These two are exactly equal and we don't have any acceleration right now. Stop writing, please listen. Stop writing, please listen here. Yeah. Right? So right now PS value and PR plus PY plus PV are both are equal, so that we can say there is no acceleration and deceleration. All of a sudden, if you have one short circuit fault on B conductor, only B, line to ground fault. Because of this line to ground fault, definitely PV value will become 0. PV value will become 0. Then what will happen to the accelerating power in this case? Accelerating power is mechanical input PS. What is the electrical power output? PR plus PY. And you have PV value 0. PR plus PY and PV value was 0, you can see. Okay, done. Now, how is this accelerating power? Is it positive or negative? Tell me, please. How is that accelerating power? Positive. Good, positive. We have an acceleration. Okay. See, but you see how this current is circulating. It's going to ground and circulating in this manner, right? Circulating in this manner and going out, whatever it is. But if you are capable to keep some resistor, listen kindly. If you are capable to keep some resistor in that fault current flow path, if you are capable to keep some resistor, definitely some amount of power will be consumed by the resistor also. And who has to supply that power? Obviously, generator. Means not only this PR and PY, whatever the power consumed by the resistor, that's also going to be supplied by the generator. So net electrical power delivered by the generator will increase. So net electrical power is increasing means I can say accelerating power will come down and system stability is going to be improved. So have you understood this? I will repeat it with a diagram. Kindly observe. So simply what I am suggesting here is we have to keep some resistor in the fault current path. In that way, I am going to ground this neutral of the generator with a resistor. So that we have some loss in the resistor. That loss has to be supplied with a generator. Okay, so I'll say in the next slide. Next slide, kindly observe. Second one I'm saying. So it's a generator. Like this we have. And this is a resistor we connected from that neutral to ground, Rn. And this is RYB. And this is a short circuit we said. And we have a fault current of IF that is circulating its path through Rn resistor. Rn resistor. And you know, here we have PR and PY. PY. Now, what is the accelerating power in this case? Accelerating power in this case is mechanical input. Anyhow, you know, PS value only. Mechanical input is remains same as PS. But what is the electrical power output? PR plus PY. Of course, PB is 0 plus power consumed by the neutral resistor. Power consumed by the neutral resistor. So you can call it is IF square into Rn. IF square into Rn. And this value was positive. But one thing what you can observe is accelerating power in second case is less compared to the first case. So that if you ground the neutral of the alternator with a resistor, definitely net accelerating power will decrease during grounded faults. And the system stability will be definitely improved. Okay, this is one reason why the people will suggest to go with the resistance grounding for the alternators. Okay, yeah. So I'm writing that statement, kindly go through it. If generator neutral is grounded with a resistor, generator neutral is grounded with resistor, then transient stability of system, will be improved. System will be improved during grounded faults. Okay, so during grounded faults, we can say transient stability of system is going to be improved. Let us think in the similar way with respect to motor. What will happen? So this is a grounding of generator we are discussing with respect to stability of system. Next, I am taking up with respect to motor, synchronous motor. We can say better synchronous motor. You see, this is some infinite bus bar and this is some power network we have. This is a synchronous motor having some mechanical load on the shaft. And it's a star connected motor. Neutral is connected to ground. Okay, with what grounding we'll use? That will tell me first. What grounding? You see, as you said earlier, in case of generator, resistance grounding will improve the stability. Let us take the resistance grounding here also. Then I will think whether this grounding is improving the stability or deproving the stability in a reverse sense. Okay, so I have grounded this with a resistor right now, like this. First, I will tell you with respect to healthy condition. Kindly observe. Healthy condition. Mechanical load, I will take some numbers for our understanding, clarity. PS value, let us say 200 kilowatts. Then how much is the electrical power value? That is also 200 kilowatts. And there is no current in the resistor, there is no loss in the system at all. Then definitely electrical power input, what we are giving, 200, directly transferred to mechanical as 200, and that load is going to be satisfied. Clear? Now, unfortunately, you have a grounded fault at certain location in the network. Because of that grounded fault, you know, some current is getting circulated in the ground. Means obviously this neutral resistor will be carrying some current. Having some loss in the resistor. Not only that. Listen to my words. This electrical power has been changed or decreased from 200 to some value, whatever it is. I'll take that number as 100. electrical power input suddenly fallen down from a number 200 to 100 because of this grounded fault what we have taken up in the system. Okay, see, we have some resistor, na? It is carrying some current. Definitely, it is consuming some power. Let us say it is consuming a power of 5 kilowatts. That resistor is consuming a power of 5 kilowatts. Okay, kindly observe my words. Kindly observe my words. What is electrical input? 100. Mechanical load 200. There is a power loss of 5 kilowatts. Power loss of 5 kilowatt by means of the resistor what we have shown. In that view, what I have to say is, in that 100 kilowatt electrical input you have given, 100 kilowatt electrical input you have given, 5 kilowatt is lost in the neutral resistor. 5 kilowatt is lost in the neutral resistor. Then what is the net electrical power to be converted into mechanical? What is the net electrical power to be converted into mechanical? That is the value 95 kilowatts. All of you getting my words? That's the value 95 kilowatts. Clear? Right? So in this case, you write in a concluded way. In this case, because of loss in neutral resistor, because of loss in the neutral resistor, the net electrical power input will be 95 kilowatts only. 95 kilowatts. Then what is your accelerating power here? It is 95 minus 200. It's a deceleration actually. So it is minus 105 kilowatt deceleration. Minus 105 kilowatt deceleration. For example, if you don't take a resistor here, if you take a solid ground, then you don't have this loss. Then what will happen to deceleration? Minus 100. Minus 100. All of you getting my words? So when the deceleration is more, when we have more deceleration for the rotor, if you go with a resistor grounding. So if you go with a resistor grounding, more deceleration for the rotor, then the system stability will be less. So we should not use resistance grounding for the synchronous motor. Either we have to go for a solid grounding, but to reduce a fault current value, the people will suggest to go with the reactance grounding here. If you keep a reactance, it won't consume any power. So whatever the electrical input you are giving, that will be converted into mechanical. So the net deceleration will be less. Deceleration in the rotor will be less, we can say. Okay, yeah. So I'm showing in the next slide. Next slide, kindly observe. So you write here itself, that implies net deceleration is more. Deceleration is more due to resistance grounding. Due to resistance grounding. Yeah. So therefore, generally, synchronous motor neutral is grounded with reactance. Grounded with reactance. Grounded with reactance to avoid the increment in the deceleration. Increment in the deceleration. In the deceleration. To avoid increment in the deceleration. Generally, synchronous motor neutral is grounded with the reactance to avoid increment in the deacceleration. Okay. So always it is preferable to go for generator with the resistance grounding, neutral grounding, and motor, synchronous motor with the reactance grounding in the view of system stability. With respect to system stability. Okay, so have a break for 10 minutes. have a break for 10 minutes. After break, we will be continuing with these methods to improve the transient stability of system, and then we will start the power system matrices. Okay, 10 minutes break. So I have resumed audio, video on screen. Please kindly confirm once. Yeah, fine. So let's move ahead. So actually, we discussed some methods to improve the steady state stability of system, right? That is adding the series capacitor or using double circuit line, bundle conductor system. See, as and when you are saying that steady state stability was improved by some technique, definitely transient stability also going to be improved by the same technique. So maintaining the P maximum value high, maintaining the P maximum value high, or maintaining less loading on the system will definitely improve the steady state stability as well as transient stability of the system also. Okay, so I'll write in a brief way, sixth one, using series capacitors, comma, double circuit lines, comma, parallel lines will improve transient stability of the system, right? Transient stability of system also. Because at initial P maximum value will be high, right? Initial P maximum value will be high. See, in the previous study, we are using reactance grounding in order to reduce the fault current. If you want, I'll write here. Reactance grounding to reduce fault current. Okay, let's continue. And next one. See, if you clear the fault very quickly in the system, after the fault occurrence, within very less time, if you are capable to clear the fault, definitely A1 area will come down. We discussed earlier. Then the system stability is going to be improved. Is by using fast-acting protective switchgear. System stability is going to be improved. By using fast-acting protective switchgear. Transient stability of system will be improved. By using fast-acting protective switchgear, right? Definitely, transient stability of system is going to be improved because the fault will be cleared quickly, and we will have less value of A1 area, right? Because of that, A2 max will go high, and system stability will be improved. Okay, next, eighth one. Listen here. See, for example, if you have a double circuit line here, okay, before moving to that double circuit line and all, first listen to the statement what I'm saying. Actually, the circuit breakers, whatever we are using in our system are 3-pole breakers. Circuit breakers, whatever we are using in our system are 3-pole circuit breakers in such a way that any fault occurred in the system, is it LG, LL, LLG, any type of fault occurred in the system, all the 3 poles will be opened simultaneously. Okay, that type of system I will show. So in the case one I am showing, it is one generator, and you have 3 wires here. Like this, we have 3 wires. ABC, you can say ABC, and this is Y connected generator. Okay, next. We have a double circuit line here. So means in the circuit number 1, we have ABC conductors. Circuit number 2 also we have ABC conductors. I'll show those ABC conductors. The circuit 1, it is A1, B1, C1. It's a circuit 1 conductors. Circuit 2 conductors also I am showing. It is A2 and B2, and this is C2. Like this we have A1, B1, C1, A2, B2, C2. Now you join things in a proper way. This A is connected to this A1, and obviously this A is also connected to this A2. Next, B. B is connected to this B1 and this B is connected to this B2 also. Next, C. C is connected to the C1 and as well as it is connected to C2 also. Like this, we'll have one double circuit line running. Right? A divide into two conductors, A1, A2. B divide into two conductors, B1, B2. C divide into two conductors, C1, C2. Now, at the other end of this double circuit line, again you have some breakers. Okay. First, this is a sending end side. Sending end side. I am keeping some breaker here. This is one 3-pole breaker I will show. First, let me copy this diagram. Yeah. So it's a star grounded alternator. Star grounded alternator. I am showing one 3-pole breaker at this place. 3-pole circuit breaker. And this is a second 3-pole circuit breaker here. Second 3-pole circuit breaker. Yeah. Kindly observe my words. Kindly observe my words. Unfortunately, we have a short circuit fault on the circuit 2 conductor. Maybe it's a LG fault, LL fault, whatever. Some fault occurred. You take LG for time being. LG. So line C to ground, you have the fault. Yeah, just listen my words. Listen my words, please. Listen my words. Line C to ground fault occurred. See, tell me, in the circuit breaker number 2, what we have? Circuit breaker number 2. Is it only pole corresponding to C will be disconnected? Is it only the pole corresponding to C will be disconnected, or all the 3 poles are open? Whether all the 3 lines are disconnected, only line C is disconnected. Tell me, please. All the 3 lines will be disconnected. But still, you see, even this breaker was open, but still, this generator is capable to supply power to the infinite bus bar by the circuit number 1. By the circuit number 1, it is capable to supply with some value of P maximum. With some value of P maximum after clearing the fault. After clearing the fault, you have some value of P maximum, so-called P maximum 3. P maximum 3. For example, instead of this 3-pole breaker, if you go with single pole breakers now, you go with single pole breakers. I'll show in the next slide. See, this is the same system what we have taken earlier. It's a case 2. Case 2. I am using single pole breakers here. Single pole circuit breakers like this. Single pole circuit breakers. Now you see the thing what I am saying you. See the thing kindly. See, if you are using single pole breakers and if you have LG fault on C2, if you have LG fault on C2, which breaker will be open? Which breaker will be open? Only C2 breaker will be open. Only the breaker corresponding to C2 will be open. And A2, B2 are in contact, are in supply. Yes or no? Tell me please. All of you getting my words? Yeah. So only one breaker is going to be open. Just for your understanding, I will remove this. So that C2 line was disconnected. C2 line was disconnected. Please tell me. Please answer this one. How many conductors we have in the phase A now? How many conductors we have in the phase A? 2 conductors, A1, A2. 2 conductors in the phase A, A1, A2. For example, if you assume that phase A conductor impedance is Z, phase B conductor Z, phase C conductor Z, here also Z, Z, Z. What is the phase A impedance now? What is the phase A impedance? Z in parallel with Z, it will become Z by 2. What is phase B impedance? Tell me please. What is phase B impedance? Also Z by 2. What is phase C impedance? Z. Okay, accepted. So you can write now ZA equals to Z by 2, ZB Z by 2, ZC will be Z. Accepted. It's unbalanced. It's unbalanced. Okay. In the previous case of 3-pole breaker, all the 3 poles were open. All the 3 poles were open. See, if all the 3 poles were open, what is ZA value? You feel each conductor will have an impedance of Z. Feel that each conductor is having an impedance of Z. Please tell me, what is ZA here? Z. What is ZB? Also Z. What is ZC? Also Z. All of you getting my words? When we are thinking about these numbers, after clearing the fault by opening the breaker. See, very simple question to you. Simple question. It's a 3-pole circuit breakers diagram. Very simple question to you. Compare the case 1 and case 2. Compare the case 1 and case 2 using 3-pole breakers and using single pole breakers. Okay. In which case net transfer impedance will be less. In which case net transfer impedance will be less. Is it with 3-pole or single pole? In which case net transfer impedance will be less. Definitely with a single pole. How it is 3-pole, Sai Charan Reddy? Look kindly. Second case. If you are using single pole breakers, the net transfer impedance will be less. Then how is the value of P maximum? How is the value of P maximum in the second case? How is the value of P maximum? 3 means after clearing the fault with the single pole breakers, how is the P maximum value? Definitely more. In that particular case, we say P maximum 3 will be high if you are using single pole breakers as compared to 3-pole breakers. In that sense, definitely system stability is going to be improved. All of you getting this? So I can say by using single pole breakers, single pole circuit breakers, the maximum power transfer in post fault condition is higher compared to using the 3-pole breakers. Maximum power transfer in the post fault condition is high. For which faults? Only for unsymmetrical faults, right? Means for LG, LLG and LL. For these faults only we can say P max 3 is more if you are using single pole breakers. If you have a 3-phase fault or 3-phase to ground fault, either you are using single pole breakers or 3-pole breakers, it makes no difference. Right? Higher in bracket in case of unsymmetrical faults. In case of unsymmetrical faults. Right? That implies transient stability of system increases with single pole breakers usage. Single pole circuit breakers usage. We are using single pole circuit breakers, then we can say that the transient stability of system is going to be improved. Okay. Simple thing. So next method I will tell you. Next method to improve the system stability. Yeah, so I'm moving with the next slide. So it's our ninth method to improve the transient stability of system. Look here. So this is some generator, bus bar connected to some transmission line. And then at the end, you have some infinite bus bar. Infinite bus. Look here. See, I am connecting one shunt resistor intentionally like this. Simply, I have taken one resistor. I've taken some resistor. Yeah, so I've taken some resistor, RS shunt resistor, connected to that bus bar. Yeah, please listen. Somebody is asking again the same doubt. Sir, after fault is cleared, both cases Z/2 only, sir. So P max is same. Please go through the thing what I said here. What is ZA, ZB, ZC here? Z value. What is ZA, ZB, ZC here? Z/2, Z/2, Z. In that way, the net transfer impedance from the generator to infinite bus will be less. So P max will be more. That's what I explained. Without listening clearly, how can you question this? Yeah, let's move ahead. We have some shunt resistor bank connected at the generator, but I will keep one switch here. I'll keep one switch here, such that the switch is going to be closed. Switch is going to be closed only during the fault or only during disturbance. Any kind of disturbance, whatever it is. Maybe fault you consider for time. See, but under normal operating condition, it should be remains in open mode. Under normal operating condition, it should be remains in open mode. Okay? Yeah. Next, look here. Look here. So RSH is a shunt resistor. Sometimes we call this as braking resistor. Braking resistor. This braking resistor connected at generator bus bar, such that it will come into action only during short circuit fault or only during disturbance, such that it will come into action. It will come into action during disturbance, or you can say during short circuit fault. During disturbance, or you can say during short circuit fault. Then what's the purpose of this one? Why we are keeping this means simply, yeah, listen please. Simply, whenever we have a short circuit fault at the time, with respect to this terminal voltage, definitely it will absorb some power, right? It will be absorbing some power. So as and when it is absorbing some power, who has to supply that power? Definitely generator has to supply it. So in that case, definitely we can say net electrical power output during short circuit fault will be more, and net accelerating power will be low, and system stability will be improved, we can say. Very simple thing, very simple thing. Just we connect a resistor at the generator location. Whenever you have a short circuit fault, it will be connected onto the bus bar, absorbing some power. It is absorbing some power, and that has to be supplied by the generator. Net electrical power output by the generator during fault will be more, accelerating power will be less, system stability is more. Okay, right. So that implies during short circuit fault, power drawn by shunt resistor is more. Power drawn by shunt resistor will increase. Okay, so you can say electrical power output will be increased. Yeah, that implies accelerating power will be less, transient stability of system will be improved. Transient stability of the system will be improved. Yeah, here, what I said regarding the terminology post-fault here, what I said regarding terminology post-fault, is it during fault or after clearing fault? Post-fault means what here in the stability analysis? Is it during fault or after clearing fault? Tell me please. After clearing fault, many are answering this one. Post-fault in the stability analysis means after clearing the short circuit fault. In case of fault analysis, if you find a term like post-fault, that will be during fault. Okay? Yeah, let's continue. RSH will come into act during fault. Next, see, but for this switching action, switching this resistor into the system or disconnecting the resistor from the system, right? To take up that one, we have to use some electronic switch here. Electronic switch, maybe you can say we have to use some sort of power electronic switch, right? So I will be showing that switch along with the resistor now. This is one switch I am showing. Something like this. So this is one resistor. so-called braking resistor, and it is connected to the bus bar. So this is simply AC switch, back-to-back connection of thyristors. And according to our requirement, we are going to give firing pulses to this, and we are capable to control this one also. And this we are going to name as thyristor controlled braking resistor. This element is connected at the generator location. Thyristor controlled braking resistor. Braking resistor. Thyristor controlled braking resistor. TCBR. TCBR. Yeah, you asked your doubt in a doubt session, anonymous attendee. Yeah. So this is one of the equipment which will be used to improve the transient stability of the system. Same thing, but we added one switch here in the power electronic manner. Right. So this ends the transient stability analysis. Of course, total power system stability analysis. Now we will be starting with the what we call power system matrices. Next chapter. Power system matrices. Yeah. Tomorrow, we have class from 7 to 12. Tomorrow we have a class from 7 to 12. And then we have one more class, maybe induction machine from 5 to 9 evening. 5 to 9. Anyway, I will write at the end also. After completing this class, I will write that schedule. For time being, somebody is asking me, that's why I'm saying. Tomorrow morning, 7 a.m. to 12 p.m. We have this power system analysis class. And then we have one more class in the evening time. That is 5 p.m. to 9 p.m. induction machines. Do we use single pole circuit breakers? Yes. Manish Kumar Bhagat. At some places we are using. Single pole breakers. At some places, particularly if you have double circuit lines, at those places the people are proposing to use. Yeah. So I'll take one more what's called 5 power system matrices. Tomorrow it won't be completed. We'll take one more Sunday, 7 to 12. We'll take one more Sunday and we'll complete the syllabus. Yeah. So this is our next chapter, power system matrices. So before moving ahead of these matrices construction and all, particularly bus admittance matrix and bus impedance matrix, we are going to call Y bus and Z bus. We are going to say generally Y bus and Z bus. First, I want to tell how we are going to represent each and every element in this Y bus and Z bus constructions. Right? First element you have generator, of course. Right? So how you are going to represent generator in the generator? How we are going to represent generator in the Y bus and Z bus constructions? Means it's going to be represented as a current source, not constant, simply current source in parallel with its internal impedance, right? Represented as current source in parallel with its internal impedance. Internal impedance in parallel with its internal impedance. Okay, means I will be showing this current source symbol, and we are keeping some impedance of the generator ZG. But what impedance you should take for this generator? What impedance we should take for this generator? Is it steady state impedance, a transient impedance, or subtransient impedance? That depends upon for what purpose you are constructing the matrix. For example, you are constructing these matrices to do power, what we call fault analysis. I have to take this value as XD double dash. Subtransient impedance you have to consider. For example, if you are constructing this matrices to do load flow, so-called steady state, we should take the steady state impedance here. And if you are constructing these matrices to do transient stability analysis, at the time we should take the transient impedance. See, one more thing, what I want to tell in the initial stage itself is, what is the purpose of constructing these matrices, Y bus and Z bus, is to make the large power system network analysis as easy. To make the large power system network analysis as easy, we have to construct these matrices. Okay, I will write that statement in the starting slide itself. To do large power system network analysis. Power system network analysis. Okay, what do you mean by this large power system network analysis? What are the analysis we are discussing now? One is fault analysis, next stability, and then load flow. If you want to do these three analysis on a big level of power system network, we need to go with these matrices for easiness. Okay, now next. How you represent a transmission line and transformer? Transmission line, sometimes it can be represented as a pi model, or it can be represented as a series impedance. That depends upon our study. Okay, either pi model you can take, or you can take this as short line model. Either you can take this as pi model, or you can take that as short line model. Whereas transformer, it is represented as a series impedance only. Transformer represented as series impedance. Represented as series impedance. Represented as series impedance. Okay, next thing. Let's continue with these matrices. First, before talking about exactly Y bus and Z bus, I'll take one simple some network with some nodes, branches, and all. I'll try to write KCL equations from that. Okay, yeah. So let's see in the next slide. So I'm taking some example network. With this network only, I'm going to tell many things to you. Example network I'm taking up. So this is node 1, and we have some branch impedance like this. Right? So like this we have, and I'm showing some current sources here in this network. In this network, I'm showing some current sources. Right? Some I1 current source, and here I am showing one current source as I2. And these are some nodes I am showing. It's the node 1 and node number 2, and it's a node number 3. Node number 1, 2, 3, and these are node number 0. Reference, you can say 1, 2, 3, and then 0. Reference. And these branch impedances I am showing now. Admittance I will show. Rather than impedance, I am going to show these things as admittances. It is Y10, Y12, Y23, Y20, Y30. These are the admittances of the branches. Admittances of branches. Okay. And these node voltages I am indicating here. Node 1, V1. Node 2, V2. Node 3, V3. And reference is 0. Reference is 0. Simple. You apply KCL at this node 1, node 2, node 3. Write down those KCL equations first. KCL at node number 1. KCL at node number 1. What is the current injection to node 1? What is the current injection to node 1? I1. I1 is a current injection to node 1. I1 is equals to. What are the outgoing currents? Outgoing currents will be this current you take. V1 minus 0 is a voltage gap, V1 minus 0 into Y1 0. V1 minus 0 into Y1 0. V1 minus 0 into Y1 0 plus. What is this current? 1 to 2 current. V1 minus V2 into Y1. V1 minus V2 into Y1. Means we can get now I1 is equals to V1 into Y1 0 plus Y1 2 plus V2 into minus Y1 2. You don't have coefficient of V3. You don't have coefficient of V3. You take this as equation number 1. Take it as equation number 1. Okay, let's say KCL at node number 2. KCL at node number 2. Make it quick, please. It's a general thing only. So I'll show you in the next slide. KCL at node number 2. What are the current injection to node 2? No current source. No current source at node 2. So current injection will be 0. What are the outgoing currents now? 2 minus 1 into Y12. V2 minus V1 into Y12, 1 current. V2 minus V3 into Y23. Next one. V2 minus 0 into Y20. So let's write V2 minus V1 into Y12 plus V2 minus V3 into Y23 plus V2 minus 0 Y20. And you take this V1 common. V1 you take common. What you get now? Minus Y12. And if you take that V2 common, what you get now? Y12 plus Y23 plus Y20. Y12 plus Y23 plus Y20 plus V3 common. And what you get now? Minus Y23. V3 common, that will be minus Y23. So this is equation number. Okay, V1 into minus Y12, V2 into Y12 plus Y23 plus Y20 plus V3 into minus Y23. That's the equation. Next, KCL at node number 3, you tell me please. KCL at node number 3. What you can say? Node number 3. What's the current injection? I'm sorry, you take it as I3. Because node 3, no. Follow the notation. Follow notation. I3 is a current injection. What are the outgoing currents? V3 minus V2, Y23. V3 minus 0, Y30. So you can get I3 equals to V3 minus V2 into Y23, V3 minus V2 into Y23 plus V3 minus 0 into Y30. That's it. Only these two. And you can write now I3 is equals to, you don't have coefficient of V1 here. Don't have coefficient of V1. And you have coefficient of V2 minus Y23. And what are the coefficient of V3? You can write Y30 plus Y23. V3 coefficient is Y30 plus Y23. You can say this is equation number 3. Now, simply you take up the equation 1, 2, 3 into matrix form. Take up the equations 1, 2, 3 into matrix formation. Yeah, let's move ahead. Let's move ahead in the next slide. So equation 1, left side term you take I1, second equation 0, third equation I3. So you have I1 0 I3, I1 0 I3 is equals to, you'll get some matrix here with coefficients as V1, V2, V3. Coefficients V1, V2, V3. What are the coefficients of these V1, V2, V3? Y10 plus Y12 minus Y12 0. Y10 plus Y12 minus Y12 0. Next, second equation. Minus Y12 and you have Y12 plus Y23 plus Y20. Y12 plus Y23 plus Y20 and you have here minus Y23. Next, here you have 0 minus Y23 and you have Y30 plus Y23. Y30 plus Y23. All of you getting this? Like this? Are you getting these matrices? KCL equations 1, 2, 3, we are reframing into some matrix. All of you getting this or not? Nobody is responding. Are you clear? Yeah, you please tell me, what is this left side matrix you have? I1, 0, I3, na? I1, 0, I3. What is that I1, 0, I3? These are bus current injections. Bus current at 1, bus current at 2, bus current at 3. So this is a bus current injection vector. Bus current injection vector. Bus current injection vector. You can write it as IBus. Bus current injection vector. We are writing it as IBus. Okay, next. What about this V1, V2, V3? V1, V2, V3 are nothing but node voltages here. Bus 1, bus 2, bus 3 voltages, or you can say node voltages. You can call this one as bus voltage vector. Bus voltage vector. You name this as VBus. Bus voltage vector, you can name this as VBus. And whatever the relationship you have between this bus current injection to bus voltage, whatever the relation you have between bus current injections to bus voltages, that matrix we are going to name as bus admittance matrix. This matrix we are going to name as bus admittance matrix. So you name this as YBus. Name this as YBus. Bus admittance matrix, you can call it as YBus. So from this you can write IBus is equals to YBus into VBus. IBus equals to YBus into VBus. So I'll show you in the next slide. Bus current injection vector is equals to bus admittance matrix into bus voltage vector. Bus voltage vector. And if you have sizes, first one 3 by 1, second one 3 by 3, third one is of 3 by 1. 3 by 1, 3 by 3, and then 3 by 8. What is that 3 here? What is the 3? What is that number 3? Number of nodes you can say, excluding reference. Excluding reference. Number of nodes excluding reference. Nothing but in our power system terminology, it will be the number of buses in the system by taking ground as a reference or by taking neutral as a reference. So 3 will be the number of buses, or you can say number of nodes. What will be the size of this YBus we are getting now? 3 by 3. So you can call, if you have, let's say 100 buses in the system or 100 number of nodes in the network, then how many KCL equations you will get? 100 KCL equations you will get. Then what is the size of YBus? 100 by 100 cells. 100 by 100. Okay. So now you can say for n bus system, size of bus admittance matrix will be n by m. For a n bus system, size of bus admittance matrix will be n by m. Number of buses by number of buses you can say. So if you want me to write that equation in the form of n bus, you can call bus current injection vector is equals to bus admittance matrix multiplied with bus voltage vector. So bus current injection vector, it is n by 1 size. YBus n by n size. VBus will be n by 1 size. VBus will be n by 1 size. Okay. Now you do one thing. Multiply with YBus inverse on both sides. Multiply with YBus inverse on both sides. YBus inverse on both sides. Okay, so if you do that, obviously you can get YBus inverse is equals to, YBus inverse into IBus is equals to, obviously YBus inverse into YBus inverse will be identity matrix. It will come to be simply VBus. So bus voltage vector equals to YBus inverse into IBus. Bus voltage vector is equals to YBus inverse into IBus. Whatever that YBus inverse we have, YBus inverse, that we are going to name as ZBus. Or you can say bus impedance matrix. Yeah. So let's write to the next slide. Bus impedance matrix. Bus impedance matrix Z bus is nothing but inversion of the Y bus matrix. Inversion of the Y bus matrix. Inversion of the Y bus matrix. Right? Means what's the size of this Z bus here? What's the size of Z bus? Size of Z bus will be obviously of the size n by n, as a Y bus is of the size n by n. Of course, you know, bus voltage vector V bus is equals to bus impedance matrix Z bus into bus current injection vector I bus. Like this you can write, just for the what we call understanding sake, I have rewritten the matrix what we got here. Z bus into I bus equals to V bus. Means I have written V bus equals to Z bus into I bus. And sizes of these matrices, if you call n by 1, n by n here, it is n by 1. N by 1. Okay. Clear? Next, one more property I will observe from the Y bus matrix what we have constructed. From the Y bus matrix what we have constructed. Just observe this this thing. These are bus numberings you can take. Buses 1, 2, 3 here. Here also you can say 1, 2, 3. How this matrix looking to be? How this matrix looks for you? Please tell me. How this matrix looks to be? For the transpose of this matrix, it will be remain same, na? Because you know the first row and first column same. Second row, second column same. Third row, third column also same. See, whatever the Y bus matrix we have here, that is a symmetric matrix. Y bus matrix is a symmetric matrix, right? Symmetric matrix. Y bus matrix, it's a square symmetric matrix. Square symmetric matrix. What about Z bus? What about Z bus? See, this you might have studied in your linear algebra classes. Linear algebra classes. Like if matrix A is a symmetric matrix, matrix A, if it is symmetric for you, then definitely A inverse also symmetric matrix only. If matrix A is a symmetric matrix, A inverse also comes to be symmetric. In that perspective, Z bus matrix also comes to be symmetric. Of course, it's a square. So I can say Z bus matrix is also square symmetric matrix. Square symmetric matrix you can write. Z bus matrix is also square symmetric matrix. Yeah. So I think all of you getting this? Yeah. So we will start in tomorrow class with the definition of the Y bus elements first. We'll take up the heading like definition of the Y bus elements. And then we'll take the definition of the Z bus elements. Okay, after completing these things, we will start with the Y bus construction. What are the various methods to construct the Y bus? That we'll do. After that, I will discuss the Z bus briefly. And our main concentration is on how to do fault analysis with the help of Z bus. How to do fault analysis with the help of Z bus. Mostly by tomorrow, we will be finishing up this power system matrices. And then next Sunday, we have one more Sunday in the same time, 7 to 12 or something. In that time, we will finish the load flow analysis also. Okay. So I have announced the schedule already for you for tomorrow class. Tomorrow, 7 a.m. to 12 p.m. our F&S power system analysis, and then 5 p.m. to 9 p.m. Let me check. I think it is an induction machine only, but let me confirm once. Yeah, induction machine. Induction machine. Okay. So if you have any doubt, you can raise your hands. First, I will make all the hands low. You can raise your hands now. Sai Charan Reddy.
Hello, sir.
Tell me, Sai Charan.
Sir, in these cases, sir, we studied about some cases, sir.
Yeah.
Stability analyzing cases. So,
Hmm,
for that, we don't have more examples, na, sir. Oh, means,
More examples means?
Like previously.
Those previous gate questions only the complete reference. At least
Okay.
in each and every case study, you used to get 1 or 2 problems.
Yes, sir. Yes, sir.
Particularly line removal is a more famous area. They asked,
Yes,
I
sir.
think, regularly some 4 to 5 questions till now in the gate exam.
Yes,
So
sir.
thoroughly practice the previous gate questions. That itself is our reference. And anyway, I provided some questions extra, no, that you try
Yes,
to
sir.
practice.
Yes, sir.
Yeah.
Sir, here you multiplied with y bus inverse, na, sir. In both. There we don't get identity matrix, na, sir.
Y bus inverse into y bus will be identity, right?
Yes.
That I have
Identity
removed.
mean
Identity multiplied by V bus will be V bus only. Na?
V bus only. Oh, yes, sir. Yes.
That's why I have written directly.
Okay, sir.
Yeah. Any other doubt here, Sajan?
No, sir. No, sir.
Yeah. Viraj.
Hello.
Tell me, Viraj.
Sir, there is a question in our workbook, sir, volume 2. It is saying that there are 2 machines. They are not saying they are identical machines or nothing. There are 2 machines. What are the cases of M equivalent? They gave answers like 1, 2, 3, 4.
It will be 2. Machines swinging together is one case. Machines not swinging together is the second case.
But they gave answer 3, sir.
It won't come 3, I think so.
That's why I'm asking, sir.
Only 2.
Only 2, na, sir? Okay, sir.
Yeah.
And second one is, sir, general doubt, sir. Whenever a power cut happens, means due to some fault at the rainy season, anything in your distribution lines, then that case, how when power is when we are giving back power at that condition, the power will come back and come means on and off will be taken place, na, sir, due to auto recloser.
Yeah.
It will check whether system is okay. It will on, and sometimes it will trip back. Why these things happen, sir?
Because majority of the faults what we have in the system are temporary faults.
Yes, sir.
So if it's a temporary fault and if you open the breaker permanently,
okay, sir,
you are losing your reliability of the system.
Okay, sir.
Means you are unable to supply the load because you decided that the fault is there in the system, right?
Yes, sir.
But to identify those what we call temporary faults, it is better to use a reclosure.
Okay, sir.
If you are using a reclosure type breaker without any manual action, whatever the temporary fault you say, that will be cleared by opening the breaker.
Okay, sir.
Okay, and system regains its original mode without any disconnection.
Okay, sir.
So in that view, we will be going for that type of thing.
Yes, sir. The doubt in that is if a fault is even cleared also, is there anything with means coming from 0 to load at that time it will trip again, like that? Any condition is there?
Can you repeat again what you asked?
Sir, what I want to ask means అంటే సార్ ఇప్పుడు ఫాల్ట్ వచ్చి రావడం వల్ల ఆటో రిక్లోజర్ ఓపెన్ చేసింది సార్. టెంపరరీ ఫాల్ట్ కాబట్టి కాసేపటికి మళ్ళీ క్లోజ్ చేసి చూసేసరికి ఫాల్ట్ క్లోజ్ అయిందా లేదా, అదే ఫాల్ట్ ఓపెన్ అయిపోయిందా లేదా అన్నది చూసుకుని సిస్టమ్ పవర్ ఇస్తూ ఉంటుంది సార్.
ఓకే,
ఇప్పుడు లోడ్ ఇప్పుడు దాకా 0 ఉన్నది ఒకేసారి హై అవ్వడం వల్ల, అంటే ఇప్పుడు దాకా 0 ఉన్న లోడ్ ఒకేసారి హై అవ్వడం వల్ల మళ్ళీ ట్రిప్ అయ్యే కండిషన్స్ ఉంటాయి సార్.
యా, see at that time all of a sudden you are increasing load on the generator.
Yes, sir.
From 0 to high level you are going for rise in the what we call power.
Yes, sir.
So in that time, definitely the rotor body will make some swinging.
Okay, sir.
Yes, means delta value will continue to vary. But you see in your system, particularly for protection, we will be keeping some distance relays.
Yes, sir.
Okay, and what the distance relay will measure is only the ratio between voltage and current, means impedance. It will measure.
Yes, sir. Yes, sir.
After measuring that impedance, if it is below that set value or reach value, the relay is going to sense that as a fault and it will operate.
Yes, sir. Yes, sir.
Because of this continuous variation of the rotor angle, definitely impedance measured by the distance relay also going to vary with respect to time.
Okay, sir.
But at some point of time, because of that variation, that impedance measured by the relay may come below the reach value.
Yes, sir.
Chances will be there, na?
Yes, sir. Chances are
In
there.
that case, the relay will identify that as a fault, but still we don't have any fault on the system.
Yes, sir. Yes, sir.
Then it will operate.
Yes, sir.
So
Sir.
this we will call as mal-operation of the relay. So simply what I want to tell as a final statement is,
Yes, sir.
all of a sudden, if you are adding something to the system or deducting something from the system,
Okay, sir.
definitely there is a large real power variation or power surge.
Yes, sir.
This is what we call as power swing.
Yes, sir. Yes, sir.
Okay, because of these power swings, there is a chance for the distance relay to operate, which is
Yes, sir.
what we call unintentional.
Yes, sir. Yes, sir.
That's not required to be, but still the relay is operating.
That's why we put 3-zone protection like
No,
that.
3-zone protection and all different.
Power
3-zone protection is a backup protection. It's not to avoid the relay operation during the power swings.
Okay, sir.
Okay,
Sir,
to avoid the relay operation during power swings or to reduce that effect, it may be preferable to go for more relay, or you
yes, sir.
say
Yes, sir.
equilateral more relay,
Yes, sir. Yes, sir.
elliptical
Least
type
affected
more
by-
relay. That
least
type of
affected by
relays
power
we'll
swings.
use in order to reduce that zone of
Yes,
sorry, not zone actually. In order to reduce the what we call entry of the impedance point into the relay operating region.
Yes, sir.
If you restrict that zone, means operating zone of the relay or operating area of the relay in the
Yes,
RX diagram,
Okay, sir.
that impedance point may not enter into the relay operation.
Yes, sir.
So that the relay may not operate even though we have a power swing.
Sir, the same scenario applicable for distribution system also, sir?
Distribution system actually, how much is the power carried by the distribution system?
Less compared to transmission system, sir.
Very, very less. Huh?
Yes, sir.
Very, very less. Even though we have a power swing, we don't have a severe power swing on it.
Okay, sir.
So that you no need to bother about the power swings occurring in the distribution system because operating power level of the system itself is very, very low.
Okay,
But
sir.
whereas in case of long transmission lines and medium transmission lines, as the power levels are in the order of hundreds of megawatts and tens of megawatts, definitely we should think about the power swings.
Okay, sir.
Okay.
That's it.
Yeah, fine. Suryan.
Hello, sir.
Tell me, Suryan.
Sir, in 418 F, sir.
418.
Sir.
Okay. Tell me.
Sir, this. No, sir.
Tell me, Suryan.
No, sir. We have written some methods, no, sir, to improve transient stability.
Okay.
In that, the high damping created by connecting flywheel to the
flywheel.
rotor.
Yes.
How,
Flywheel.
sir, the damping will be?
Flywheel in the sense simply a large wheel connected to this rotor shaft. For example, if the rotor shaft you assume, for this rotor shaft, we used to connect a large wheel such that it won't attempt the speed variations. It won't accept the speed variations very quickly.
Okay, sir.
Because of that wheel and air, windage, many effects we have, right?
Okay, sir.
Right. So it may not allow to vary the speed quickly. So that's the thing what we are saying as damping.
Okay, sir.
Yeah. Any other doubt you have?
No, sir, that's all, sir.
Yeah. Imtiaz.
Good evening, sir.
Tell me.
Hello, sir.
Tell me, please.
Sir,
Imtiaz.
I have doubt in critical points, sir. In critical clearing angle.
Okay. Okay. What's your doubt?
Sir, in that you wrote sir, TC is less than TCR.
Yeah.
Sir, in delta C less than delta CR means the A2 maximum will be less compared to A1, no, sir.
A2 max will be
Less compared to A1.
greater, no? Delta C less than delta CR.
Means the delta CR is less.
You are clearing the fault well ahead of delta CR.
Then A2 max will be.
A2 max will go high.
Sir, so from the figure, figure we have delta CR more means we are go right side, no, sir.
Delta C is less compared to delta CR is a fixed angle for a given system and with a given disturbance. Imtiaz,
Sir.
you assume delta CR 85 degree. What do you mean by that? If the fault is cleared at 85 degree, A2 max equals to A1.
Yes, sir.
If the fault is cleared at 80 degree.
Before.
Before. That's the delta C clearing angle 80 degree now.
Yes, at the time the A2 max will be more, sir.
Then that's what it's saying, right?
Yes, I thought delta CR means more means at that time the A2 max will be less. From that graph, sir.
Not A2 max. Not you fix the delta CR to some value. Then you vary your clearing angle. First you get a clarity between these two. What is critical clearing angle?
At that time we reaches the maximum value, sir.
Listen, what is critical clearing angle?
Before rotor we can clear the fault, sir.
Before reaching to that angle, we should clear the fault.
Yes, sir.
What is clearing angle?
It clears at fixed point.
That's the angle at which you are clearing the fault.
Yes, sir.
Okay. The angle at which you are clearing the fault should be less than critical clearing angle.
Okay, sir.
The angle at which you are clearing the fault is delta C. Critical clearing angle is delta CR. Delta C should be less than delta CR.
Yes, sir.
Okay, tell me, for example, Imtiaz.
Yes, sir.
Critical clearing angle of a system is 86 degree.
Okay.
Fault cleared at 82 degree. Okay.
Okay, sir.
What is clearing angle?
86.
That's where you have a doubt. What is clearing angle?
Clearing means it's cleared the fault
At how much angle the fault was cleared?
82.
Means what is clearing angle?
82.
Clearing angle is 82 degree. What is critical clearing angle?
At maximum angle we clear the fault, sir.
You tell me the number.
86.
86. That's it. Those two are different numbers. We have to understand. Those two are not same.
Okay, okay, sir.
Okay. And your clearing angle should be less compared to critical. Then the system is stable.
Okay, sir.
Okay. Yeah, Sunanda, you asked me your doubt now. Please raise your hand, Sunanda. Sunanda, are you there? Please raise your hand. Dinesh.
Hello, sir. Good evening.
Tell me, Dinesh. Tell me. Good evening.
Sir, I have a doubt in problem, sir, in a volume 2 symmetrical fault way.
Okay, tell me.
Sir, there is a 3 generators, sir, connected at one bus.
Okay.
Sir, while drawing this positive sequence network, sir, we need to draw all three in parallel, sir.
All three in parallel.
With their sources.
With
their sources.
Their sources. Yes, correct.
Sir, when we get the equivalent from it, Sir, how sources are converted into equivalent? I'm not getting that, sir.
No, actually, see, for example, if you have a system something like this,
Yes, sir.
okay,
Yes, sir.
then this you want to convert into
Single.
single voltage source in series with the
Sir.
reactance.
Yes, sir.
What is this voltage?
That I'm not getting, sir. How we
Thevenin
calculate?
voltage.
Thevenin voltage.
That's it.
Okay, okay, sir.
What is this one? Thevenin
This is
impedance.
Thevenin equivalent. That it is.
That's Thevenin equivalent
Yes.
only you have to find. Positive sequence Thevenin equivalent, negative sequence Thevenin
Okay.
equivalent, zero sequence Thevenin equivalent.
Sir, I have one silly doubt, sir. Can I ask?
Tell me.
Sir, when we hang any transmission line, then
Hmm.
we get a shock, sir. But there is no path for current, sir, when we are hanging it.
See, for example, you see, what's your name? Dinesh, right?
Yes, sir.
If it is a 400 kV by √3 conductor, okay,
Yes, sir.
per phase
Yes.
voltage, it's operating at a voltage of 400 kV by √3.
Yes, sir.
It's a ground.
Yes.
Ground. Let us say this height between that ground and conductor, how much? We'll assume this, let's say 30 meters,
30 meters. Okay, sir.
somewhere 30 meters height.
Hmm.
So definitely there will be some capacitance formation between these two, na?
Okay, yes, sir.
Else. You see simply like this. It's a conductor operating at some voltage,
Yes.
producing some electric flux.
Yes.
For example,
sir.
if you are a man standing at this
Yes.
place, let us say, right? Whatever the
Hmm.
electric flux produced by the conductor will be touching you,
Yes. Cutting
touching
and
you.
current induced
And what is the rate of change of electric flux?
very high, sir.
Current.
Yes, current.
Rate of change of electric flux is current.
Current.
Electric
Yes.
flux linkage.
Yes, sir.
So current will pass through you.
Okay, sir.
But at which plate you are standing? Zero potential plate.
Hmm.
Okay.
Yes.
But if you go
Yes, sir.
towards this one, and you will be touching the conductor, and you will be a part of conductor, right?
Yes. Yes.
Now
Sir.
between you and what we call ground, there is a capacitance formation.
Okay, sir.
Whatever the current we say, so-called charging current, may pass through you also.
Okay, sir.
That may create a shock.
Okay, sir. Getting,
But
sir.
the
Thank you,
people
sir.
will say because of high electric field intensity, we are getting a shock. Not exactly by electric field intensity, you should say because of charging current flow in you, we are getting a shock.
Okay, sir.
Okay.
Okay, thank you, sir. Getting.
Yeah. Any other doubt here?
No, sir. No.
Yeah. Pratyush.
Hello, sir.
Tell me, Pratyush.
Sir, in case of synchronous motor, damping can be reduced by using damper bars in the rotor circuit, no, sir. Due to damper bars, we have a relative speed between synchronous and rotor, then EMF induced, and that force will be there, no, sir. But how it in case of synchronous generator, as the NS and NR both are decided by only rotor, no, sir.
NS and NR?
Means NS and NR both are decided by rotor, no, sir. Rotor speed, no, sir. How the rotor will cut the stator magnetic field, that is only, no, sir, NS magnetic field.
But you are connecting that to the other machine, right? Infinite bus bar.
Yes, sir. But it will draw it will take the power from rotor circuit only, no, sir, for creating magnetic field.
No, rotor circuit is creating magnetic field.
Yes, sir.
Causing an induced EMF.
Yes, sir.
Causing some current flow.
Yes, sir.
That current is deciding the stator magnetic field in the air gap.
Yes, sir.
What is the frequency of that stator magnetic field? It is decided by the current.
Yes, sir.
Who is deciding the current? Potential difference.
Yes, sir.
Potential difference means one voltage is at its own frequency, induced EMF.
Yes, sir.
Other voltage might be at a different frequency, right?
Okay, sir. But the bus bar frequency, it may be there.
It will be there. That will be showing effect on current. That will be showing effect on magnetic field. Not induced EMF. Induced EMF might be decided by your rotor speed.
Yes, sir.
But whatever the current flowing in the stator, that is not only decided by its own frequency of induced EMF, it will be decided by the other bus frequency also.
Okay, sir.
Then stator rotating magnetic field depends upon both frequencies.
Okay, sir.
Hmm.
So then how it will be induced in damper, means how the operation will take place in damper bars, sir, when there is a fault, when there is transient condition? How there will be EMF induced in damper bars, sir, due to transient condition?
Very simple. When we will have induced EMF in the damper bars?
Relative speed between two fields.
That relative speed will exist, right?
Yes, sir.
Then definitely there is an EMF induced in the damper bars.
Means rotor speed is reduced in what
Rotor
about
speed you leave aside. Your doubt is like this, what I am saying.
Yes,
Sir, you say rotor is rotating at, let us say, 1490 RPM.
yes, sir.
Okay. Rotor is rotating at a speed of 1490 RPM. See, if it is rotating at 1490 RPM, with respect to this speed, it will cause an EMF induced.
Yes, sir.
And as the EMF is induced at a frequency with respect to this one, definitely the stator rotating magnetic field will have the same frequency.
Yes, sir.
Then you don't have any EMF induced in the damper bus.
Yes, sir.
Then it won't provide any damping. That's
Yes,
your
sir.
doubt.
Yes, sir.
Now what I am saying is, these are two machines connected. Okay.
Okay, sir.
First one is having an induced EMF E1 at some frequency F or F1, you say. F1.
Okay, sir.
Second one is having an induced EMF E2 at some frequency F2.
Yes, sir.
And this rotor is rotating at a speed of N1.
Yes, sir.
Okay. Now the question is, what is the stator rotating magnetic field speed? What is the stator rotating magnetic field speed? Tell me. Who will decide the stator rotating magnetic field speed? Is it F1 frequency or F1 and F2?
F1 and F2, sir.
Why?
Because the stator current flow is depending upon both
frequencies.
Yes, sir.
Then the stator RMA frequency speed definitely not equals to N1.
Yes, sir.
It may be more than N1, less than N1 also.
Okay, sir.
Okay.
Okay, sir. So when there is no fault, yes, sir. When there is no fault, both the frequencies and rotor frequency and busbar frequency are same.
Same. Then you don't have any EMF induced in the damper bus.
Okay. Okay, sir.
Then your frequency of your current flow is also remains same.
Okay, sir.
Okay,
sir. Yes, sir. Understood, sir. Thank you, sir.
Sunanda.
Sir, can you hear me, sir?
Tell me, Sunanda, what's your doubt? You asked many doubts in
yes, sir.
Q&A.
I have a problem and also a doubt in the last.
Okay, what's that problem here?
That's what I was typing, sir. It's there in the bits and bytes book.
Okay, please read once.
Okay, sir. A synchronous generator of reactance 1.5 per unit is connected to an infinite busbar system.
Okay.
V is equal to 1 per unit. Through a line of transformer of total reactance, it is 0.5 per unit, sir.
Okay.
The no load voltage of the generator is 1.1 per unit.
What is asking ultimately?
They are asking the frequency, sir, system frequency. Frequency of oscillation.
For small disturbance.
Of the, yes, sir, for small disturbance.
Okay. See, we discussed one formula for frequency of oscillations for small disturbance.
Yes, sir.
1 by 2 pi square root of K by M for undamped system.
Yes, sir.
Simply you substitute the numbers, you will get it right. What is K? P maximum cos delta naught. Okay. What's M? Whether all the numbers are given in per unit form?
Yes, sir. Yes, sir.
You take it in radian per unit. H by pi f.
Okay.
Second square by electrical radians.
Okay, sir.
And this unit will be per electrical radian.
Okay, sir.
Okay. You substitute the numbers, you will get it.
Okay, sir. Then the other doubt is in the last part, sir. You said no, sir, in the Y bus matrix. I bus is equal to Y bus into V bus. In Y
Yeah.
bus, it is a square matrix, sir. But how it is symmetrical, sir?
What do you mean by symmetric actually?
Both. I mean, transpose
A
are the,
transpose equals to A.
yeah, yes, sir.
That's it. It will be satisfied, na?
But Y10 plus Y12 and Y23 plus Y30 is not.
See, it is Y11, Y12, Y13, Y21, Y23, Y33.
Yes, sir.
Correct. Y2, Y22, Y2, Y21, Y22, Y23, and then 31, 32, 33.
Yes, sir.
Okay. When we will say this matrix is symmetric? When it is symmetric?
When A transpose, I mean, Y11, Y21, Y31 is equal
Y12 is equals to Y21.
to.
These two numbers should be equal.
Yes, sir.
Y13 should be equals to Y31.
Yes, sir.
Means diagonal elements should be matched. That's it.
Okay, sir.
Then you can say it is symmetric. Not the, sorry, off diagonal. Off diagonal elements should be matched. Y32, Y23 should be equal.
Okay, okay.
Okay?
Okay,
Now,
sir.
you no need to bother about these diagonal numbers, right?
Yes, sir.
Diagonal numbers will not be disturbed. Even you take the transpose or not taking the transpose.
Okay, sir.
Okay?
Okay, sir. That's it, sir.
Any other
Thank
doubt you have?
No, sir.
Yeah.
Hello, sir.
Swapnil, tell me.
Sir, actually, I have one doubt in stability. Sir, stability. Sir, if there is accelerating power of the any system is changing, then only we have to use equal area criteria, na? Otherwise, we can solve it by using just a formula. Is it correct, sir?
Oh, whenever accelerating power
Means accelerating power means suppose P2 is not zero in any fault. Suppose the fault is happening at the bus bar or the generator terminal. In such cases, we can solve by using just a normal formula. But if there is a question is like that, there is accelerating power is changing, like
then you have to go with solution of swing
fault
equation.
happening at the middle.
Then you have
Okay,
to go
means
with
we have
solution
to
of swing
use there
equation.
is the equal area criteria, na, sir? Okay, sir. Another question, sir. I send on the Telegram, sir. Can you see?
Tell me. What is that question?
Synchronous motor of the negligible resistance is receiving 25% of the power that is capable of receiving from the infinite bus. If the load on the motor is suddenly doubled, calculate the angle at which system is stable after making an oscillation between two possible swings.
It's a very simple question only, na?
Oh, sir,
How much is the initial power flow?
Initially is 25% of power
How much? 25% of what?
capable of receiving from the infinite bus.
Means it
I
is
think
0.25 times of
25.
Pmax.
Okay, sir.
Okay. Now what is
Yes. If the load of motor is suddenly doubled.
that? Suddenly doubled. Suddenly doubled means what the new mechanical load?
0.5.
2 times of 0.25 P maximum.
Yes, sir.
0.5 times of P maximum.
Yes, sir.
Then what is the new angle delta?
Yes, sir. How to
Sin inverse
calculate,
of PS2 by P max.
PS2 by max?
He's asking only final stable angle, right?
Yes, sir.
He didn't ask about what are the angles between which the rotor is swinging.
Okay, sir.
He asked only the angle at which the system is stable after making oscillations.
But sir, then here sin inverse of 0.5 it will be, na?
That's it. 30 degrees.
But sir, answer is about 46 point something. They have given.
That's not. He might be calculating the maximum angle there.
They
That's
actually
not
equal area. They used here equal area criteria.
Listen.
Yes, sir.
According to the question, what they asked, simply is asking, what is the final stable angle?
Okay, sir.
That's it. Final stable angle is 30 degrees. That's our answer.
Okay.
For example,
Okay,
if he is asking, what are the angles between which the rotor is swinging?
Okay.
Then
Yes.
we should take the initial angle delta naught as one limit.
Okay.
Other limit is a maximum angle that we have to calculate.
Okay. And
Okay,
that
how to
condition
calculate that maximum angle? You know,
equally
at that maximum angle seen by the rotor, this d delta by dt is 0.
Okay,
This is
sir.
what we should say. Integral of PS2 minus P maximum sine delta with respect to delta is equals to 0. Starting from delta naught. What is the delta naught?
Delta
Tell me.
naught. 14 point something.
Okay,
sir.
something.
Just-
Delta naught to
Okay.
delta max. You don't take it
Delta.
as delta max, you get some confusion. You take delta 2.
Okay, sir.
Delta 2. And you
Okay,
do that
sir.
integration, you will get a function in terms of delta 2, right?
Okay, sir.
Solve that function to calculate the value of delta 2.
Okay, okay.
So
Means,
the
sir,
rotor will be swinging in between delta naught and delta 2 continuously.
Okay, 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 sir. And
Okay.
suppose we have to find the middle angle. In that case, we have to
This itself is your middle angle, right?
okay, 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 sir.
Already this is very well known to you. Middle angle delta 1. This is that middle angle.
Okay, 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 sir. And yes, sir, got it. Clear, sir. Sir, I have also another one doubt. Sir, actually, sir, neutral current is 3 IA0 in all condition, na?
All conditions.
Or sir,
all conditions, neutral current or ground current equals to 3 times of zero sequence current. There is nothing
But,
change
sir,
in this equation.
okay, sir. Actually, I sent another question.
That may be
is
a wrong
about
answer. That may be a wrong answer. Correct it.
Okay, but they sir said that they actually calculated that they just find first phase
Not needed. Not
current.
needed, and all. Your answer will be 15 minus J24. That's it.
Okay, 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 sir. And sir, as another one question, sir. The power system is subjected to the fault which makes zero sequence component of the current equal to 0. The nature of the fault is, sir, in that condition, sir, I did not get how to.
You go for double line fault, which is ungrounded fault.
Nature.
Ungrounded fault, you don't have any zero sequence component, right?
Okay, okay, okay.
Ground
But
current
sir,
will be 0.
Okay, suppose the fault is a triple ELG fault, sir. In that case, in that condition,
See, you have to take an
IA0
option.
current
You
will
have to
be
take an option among these 4.
okay, okay.
Okay.
But sir, okay, sir. Suppose they have given that triple
Yeah,
ELG
I also
fault.
know. I also know that triple line to ground fault will not have any ground current.
Yes, sir.
I know that also. But it is an
IA0
unbalanced system.
Okay,
If it is an
IA0
unbalanced
is
system, already existing system is unbalanced.
okay, okay. And
Then ground
okay,
current you have.
so okay, okay. Means, sir, we have to just consider that. Okay, sir.
Whether
Okay.
the fault is grounded or ungrounded, that you consider to answer.
Okay, there may be a condition that there may be unbalanced system present there. We can
In that
consider
case,
like
triple
that.
LG will have ground current also.
Okay, if unbalanced system is there.
Yeah.
Okay, and sir, on the just above question, the nature of the following combination
That
fault
question
seen by the generator in the,
is LL and
yes,
LG. We have discussed it. No,
yes, sir. But sir, how I did not get, because sir,
that
for
we discussed
the
in class, right? That problem we discussed in class.
okay, sir, but
Go
from
through that. Go
generator
through that. I
side,
think last question we discussed in fault analysis. We have drawn the
okay.
delta star grounded diagram.
Okay, okay,
We
sir.
have
I
taken
will see
LG
that.
fault on one side, seen that as LL fault on the other side.
Okay, okay, and I will see that, sir. And sir, in the stability, we have to find the Pmax. In that condition, sir, why we take line voltages means Pmax is equal to EV divided by X. In that condition, we take E as a line. We also take a line. Why we did not take their phase?
You take phase voltages, you will get P maximum per phase.
Okay, and after that,
And
we
you
have
multiply
to
with
find
3, you get 3 phase.
Okay, okay. And sir, last one, sir. Sir, the question is the three-phase transmission line, as I just sent, sir. Three-phase transmission line reactance is 12 ohm per phase. Voltage of each end is maintained at 132 kV. Determine the steady state limit in megawatts. Sir, actually, I got this, but after that, sir, second part I did not get. Determine the limit of angular acceleration for the transient
See,
stability.
initially you have a power transfer of 2/5 times of P maximum.
Yes.
Initially you have a power transfer of 2/5 times of P maximum.
Okay.
0.4 times of P maximum, right?
Okay, sir.
At that point, a jerk happened.
Miss, sir, I did not get
You have
that
a rise
point.
in the power, you say. Rise in the power.
Okay.
Okay.
Then how to solve?
How much
sir?
maximum angle it can see, before which it should fall back.
Okay, sir.
So you have
But
to draw
sir-
that power angle curve like this. Okay. So this is
Okay,
your
sir.
initial value, 0.4 P
Okay.
maximum.
Okay, sir.
And then you have to raise this power suddenly to a high number like this. After rising it to a high number,
Okay.
starting from this point, it will be making some swinging.
Okay, sir.
What are the limits of that acceleration? Means this is one angle you should consider, and this is another angle you have to consider. So rotor will be swinging in between these two angles, right?
Okay, okay, sir.
Right. Delta naught already you know.
Yes, yes, sir.
And delta x you have to calculate by doing calculation.
Okay, okay. Means, sir, for finding delta x, we can use the swing equation you just told before.
d delta by dt at delta x equals to 0. Integral of PA d delta equals to
Okay.
0, starting from delta naught to delta x.
Okay.
Starting from that you calculate the angle delta x.
Okay.
Okay.
Okay, sir. Yeah. Thank you, sir. Thank you so much, sir.
Ramakrishna.
Yeah, hello sir. Good evening, sir.
Good evening, Ramakrishna. Tell me.
In the high damping is created by flywheels, no sir. So what are generally flywheels? I didn't get flywheels.
Flywheel, it's a large wheel I have shown clear. Somebody asked me the same doubt. Like this will connect a big wheel.
Okay. Big wheel, what does it do? It decrease damping or increase how?
Increases damping, right? Like this will connect.
Okay, okay, okay. Sir. So
right? It won't allow the speed variations quickly.
okay, due to its large size, so it
Large
won't.
size and in air, of course.
Okay, okay.
That windage effect will be there, huh?
Ah, yes, sir. Yes, okay. Okay. And in motor, we will use reactance grounding, no sir. So even reactance grounding has some loss in power, I think.
Why? You don't have resistor, right? It's a minor component of resistance there.
So it doesn't matter. Minor.
Matter. Very less. Very less.
Okay, okay.
Compared to resistance grounding, reactance grounding is better in the way of stability for a motor.
Yeah, compared to
compared to resistance grounding, reactance grounding is better, right?
Right, sir, right.
That comment you should take. But still speaking, reactance grounding you say, but still it will have some resistance.
Yes, sir, yes, sir. A small resistance.
Okay. Yes.
Okay.
Okay.
And next Sunday there is a ESC exam, so would you keep that class on that day? Or?
We will see. We will ask once. Okay.
Okay. Okay. Thank you, sir.
Yeah. Anybody have doubts? Please raise your hands. Anybody having doubts? Please raise your hands. So I think nobody is having a doubt. Thank you.